Buongiorno. This is working, yeah. Well, as our first speaker today, we welcome Phil Rippon, who will be talking on shrinking targets and recurrent behavior for forward compositions of inner functions.
Thanks, Sean. Is this working as well? Thank you very much. Well, first of all, I want to say a really big thank you to the organizers for the invitation to this lovely meeting. It is wonderful to be here in Pisa and to be able to, well, we haven't traveled to meetings like this for about 5 years, and it's absolutely great to be here. It's even better somehow that this is the Aula Dini. I'm sure I've been here before, but I didn't realize before it was Dini. That was the name of this place. And Dini was one of the main names that appeared in my PhD thesis. And of course, I had absolutely no idea who Dini was at the time, but so it's great to be here. Well, as you can see, this is joint work with Anna, Basso, Nuria, and Gwyneth. It's been a really nice collaboration with several papers coming out of it. It all started about 10 years ago when Anna visited the Open University, invited by David. And we talked about various things. And at one point, Anna said, surely there must be some nice way of classifying the internal behavior in simply connected wandering domains. And, you know, there was a short conversation about it. And here we are, about 10 years later, having written quite a lot about it. That's why this picture is here. It's the simply connected wandering domain, just to establish the beginnings of the stuff I'm talking about today. Okay, so in 2022, we published, the 5 of us published a paper in which we did do this classification of different types of ways internal dynamics goes on in simply connected wandering domains, pretty completely, as far as we could see. We then went on to think about what would happen on the boundaries of simply connected wandering domains. And we fairly quickly realized that that could be much more general than just wandering domains. There was a much more general context in which you can write that. And that led to a second paper, which has actually just appeared. And what I'm talking about today is further developments of that, which entirely about inner functions, because the behavior in wandering domains can be reduced to studying the behavior of not iteration of inner functions, but forward compositions of inner functions. And I'm afraid there are no parameter spaces. I apologize for the fact there are no parameter spaces, but having heard Duadi's famous quote, a variation of it would be that we're plowing in the dynamical plane, we're planting seeds, and then we hope that someone will be harvesting in the future. That's the story. Okay, so inner functions is what this is all about. So let me define an inner function. So inner function, it's a holomorphic map from the disk to itself. And the nice thing about it is all its radial limits, which exist by Fatou's theorem almost everywhere, they're all on the circle itself. So it's basically a self map of the disk, which maps the boundary to the boundary. For example, Blaschke products, finite Blaschke products, or infinite Blaschke products, all functions which are even more complicated than Blaschke products are there. And they can arise from dynamics. Okay, the classic theorem here about what happens if you iterate an inner function, or more generally a self-map of the unit disk, is that there's something called the Dangerois-Wolff point, to which all the iterates are attracted, and it might be in the domain and it might be on the boundary of the domain. And we're principally interested in what happens when it's on the boundary of the domain. On the boundary itself, well, dynamics are defined because the radial limits are defined almost everywhere, and they compose in the right kind of way almost everywhere. And there's this amazing dichotomy, which we started calling the ADM dichotomy, because it was first written down by Aronson in 1978, or proved by him. And then Doering and Magnay had a very big paper, and part of it was this dichotomy again. And it's all about iterating inner functions, and it tells you what happens on the boundary depending on the rate at which the iterates go towards the boundary. So case A, supposing they go fast enough so that this sum, which are often called the Blaschke condition, this sum is convergent, then almost everywhere on the boundary, the iterates go towards the Dangerois-Wolff point. Obviously, the Dangerois-Wolff point is going to be on the boundary in that case, and almost all points on the boundary go towards P. On the other hand, and this is a more complicated state, well, it's more complicated to prove, if the sum is divergent, and that could include the iterates not going to the boundary at all, or, well, they either not going to the boundary as a possibility, then the iterates on the boundary are, well, you can describe them in various chaotic ways, but one simple way is to say they're dense in the boundary for almost every zeta in the boundary. So there's a real dichotomy there between the types of behavior that can occur. So I say we're interested in forward compositions of inner functions, not iterating single inner functions. So we're going to give ourselves a sequence of little f's, which are inner functions, and forward compose them to make big F's. That's the difference between the big F's and the little f's, is that big F's are almost always compositions of little f's. So iteration is a special case, but one has to emphasize there is no Dangeau-Wolff point in general. If you allow yourself to choose those little f's, you can make the orbit, as we will call it, capital Fn of 0, go anywhere, basically, in the disk. So there's no Dangeau-Wolff point. However, all the points inside do essentially behave in the same way. So if you know where the origin goes, then all the rest follow along and do the same kind of thing. That requires a bit of proof, but it's straightforward. So we're not just doing this for its own sake, but they arise naturally in dynamics because, well, certainly if you think of an invariant domain and do a Riemann mapping to the unit disk, then you get conjugation to an inner function on the disk. But if you have a wandering domain and you produce Riemann maps at each stage, then you find that the action of f on the wandering domain is equivalent to forward composition of inner functions on the disk. So if you want to study the behavior of wandering domains, you need to be looking at forward compositions of inner functions. Okay, so a very natural question, once you've heard about the ADM dichotomy, is to what extent does that hold for forward compositions? And our first theorem about this, okay, I'm giving references to our papers. BFRS, that's us. 2024 means it was published in 2024. You'll see a 2024 with a little A on it afterwards. That means it went on the archive in 2024, in fact, 2 weeks ago. Or maybe only a week. Anyway, very recently. Okay, so this one's just appeared. And this is a special case of a general result. That if you have a forward composition of inner functions such that the equivalent of that Blaschke condition holds, convergence condition holds, then, well, we can't converge to the Dangeau-Wolff point, but almost all points, because there isn't one necessarily, almost all points on the boundary do the same as the orbit of 0 or the orbit of any other point inside the disk. So almost all points behave in the nearest equivalent to going to the Dangeau-Wolff point. I've written a cloud here which says this is much more general. So to start with, FNs don't have to be inner functions for this result to work. That had already been observed for iterates of self-maps of the disk by Bourdon and other authors, Shapiro, quite some time ago. But the function in our forward composition setting, they certainly don't have to be inner functions to make this work. And you can even make it more general. And I've written Dini down there because my co-authors allowed me to have a general theorem about the types of domains for which a result of exactly this type would hold, where you replace 1 minus Fn0 by the distance to the boundary. And if you want very general domains, nothing to do with wandering domains, but UNs to UN plus 1 and so on, then what you need is your UN to be smooth enough so it satisfies something called the Dini condition. Then if you don't have the Dini condition, you still get a theorem, but you have to have a power in there, like a half or something to guarantee the result holds. Okay, so part A of the dichotomy works very nicely. And the proof is essentially the same as the original one, although when you look at this and this, you can't quite see the resemblance, but it's basically the Borel-Cantelli first lemma, which is behind it. But part B of the dichotomy fails. And it's very easy to see that. Inner functions include Möbius transformations. If you look at examples with Möbius transformations, you can make them do almost anything that you didn't want to happen for your functions. And you can certainly, well, this is an example which is non-Möbius, which is a little harder to produce. What does it do? Well, the orbit goes to the boundary so that the sum is infinity. inside all the iterates go to 1, and on the boundary, all the iterates go to 1 for all zetas near the point 1 in an arc around 1. And that's completely the opposite type of behavior from chaotic behavior, which is what you'd like to have if you have this condition holding. So the example, the actual FNs are suitably chosen ANs, but you'll recognize, I'm sure, that if the ANs were all equal to a third, you'd have a parabolic point on the boundary. And here we've got a sequence of non-parabolic points, but getting more and more parabolic in the construction. Okay. Once you've got this example, you realize every time we tried to produce an example like this, it failed to have a property called contracting. Certainly the Möbius examples weren't contracting. So what is contracting? Well, in this context, contracting, in our context, contracting means that the hyperbolic distance between all pairs of points in the domain along the orbit tend to 0. So that's contracting. For our compositions, that's independent of which pair you choose. If it happens for one pair, it happens for all pairs. If those capital FNs were not compositions, but just sequences of self-maps of the unit disk, then different behavior. You could have contracting for some pairs and not for other pairs. But for compositions, it's a common property for all of them. Okay, so in this paper that just appeared, the second paper, we asked the following question. Because we couldn't produce contracting examples which went wrong, we asked the question, if the sum is divergent and it's contracting as a sequence, then do we get the bad behavior on the boundary? Are the FNs dense almost everywhere in the boundary? And a sort of piece of evidence for this, not just that we couldn't produce an example, but that if you go back to the case of iterates, then when you have that sum being divergent, then the sequence of iterates is contracting. So it seemed like a sensible hypothesis to choose. Before I go to the next slide, I should say that I'm now going to be talking about the latest paper, which went on the archive a couple of weeks ago, as I say, just as this one appeared with that question in it. And the latest paper going on the archive points out that the answer to this question is no, because we've managed to get cleverer examples since then. Okay, so let me tell you what positive results, what can we prove to get sufficient conditions for this bad behavior on the boundary? Well, this is all expressed in terms of something called shrinking targets. And I think the first people to introduce this name, or maybe, but not the concept, perhaps, were Hill and Sanjivalani in 1995 in connection with a dynamical problem. A shrinking target for us, there are various definitions out there, is a sequence of arcs on the boundary of the unit disk. And their lengths tend to 0, not necessarily monotonically, but often monotonically. And they don't have to be nested. So the classic example, you'd have a nested sequence, but they don't have to be nested in this definition. And then our sequence of functions Fn on the boundary hits the shrinking target. That means that Fn of zeta lies in In infinitely often. So it sort of can go all over the place, but it hits this target infinitely often. Modulus of In will either mean the distance between two numbers or the length of an arc, depending on what's inside the modulus signs. Okay, so back in the wandering domains paper in 2022, we'd already been studying forward compositions of self-maps of the unit disk. And we characterized contracting, because that was part of our characterization of behavior inside wandering domains, that Fn is contracting if your little Fn's all fix 0, if you normalize them so they all fix 0, then Fn's contracting if and only if basically the product of the lambdas tends to 0, which is equivalent more usefully in our situation to the sum of 1 minus lambda n's infinity. In future, I'm going to define 1 minus lambda n, I'm going to call it mu n. So if mu n's start appearing and I forget to tell you what they are, they're 1 minus lambda n's in future. Okay, so we have a theorem here about hitting shrinking targets. And the key thing to emphasize is this, here we have uniform contraction. So these functions contract in a very strong way in that all the little fn's, their derivative at 0 is bounded by the same constant lambda less than 1. So there's a sort of geometric nature to their contraction. They all fix 0. Their derivatives less than or equal to lambda, and In is any shrinking target for which the sum is divergent. So this is the sort of equivalent, if you like, of the 1 minus mod Fn0 is divergent, as you'll see later. Then in that case, Fn zeta hits the target for almost every zeta in the boundary. So this is not just one target, it's any target for which that sum is divergent. So if you've got the sequence of functions, you can take any target for which that sum is divergent, and we hit. So this is uniform contraction. I'm going to outline the proof of that on the next slide. So I'll repeat the statement, possibly. Yes, I will. And I've got a cloud there. After we proved this, we found that Fernandez, Melian, Pestana had proved a very similar result, but for iterating a single inner function back in 2007. And they did it as a sort of strong version of the Poincaré recurrence theorem, was what they sold it as, that if you're thinking about the Poincaré recurrence theorem and you're looking at boundary values of inner functions, then you're going to get more than you would normally get in the Poincaré recurrence theorem. Okay, so obviously their results a special case of this just by taking iteration of a single inner function. Our proof was somewhat similar to theirs in that we use one of the results that they use, but it's slightly different in some respects, but the idea is the same. Okay, so I'm going to say something about the proof. The proof outline. Okay, so the fact that we're fixing 0 means that the maps are measure preserving on the boundary. That's something that is sort of key. If you take one of your arcs, In, you look at its preimage under capital Fn, and that's what you want to look at because you want to be looking at points that will, under Fn, hit In. Then the length of that is the same as the length of In. So you can replace the sum of In being divergent by the sum of the preimages of In under the appropriate Fn being divergent. And what you want is that the set of zeta is such that zeta lies in infinitely many of those preimages, so that the forward versions will lie in infinitely many INs, has full measure. Well, this is a sort of classic Borel-Cantelli 2 situation in which ideally you would like these preimage sets to be independent. As the sum of their lengths is divergent, you'd like them to be independent, and then you'd be able to say that almost all points lie in infinitely many of them. But it's unlikely, well, it's not true in general, that they will be independent. So you have to look around and find versions of Borel-Cantelli 2, and there are many out there if you search for Borel-Cantelli 2. And the one we alighted on was due to Philip, which unusually, given the time Philip, I find very difficult to imagine that it can be spelt that way. But anyway, Philip back in 1967. But there are quite a few versions of this. So here you have some measurable sets. The sum of their lengths is infinite. And then you have a sort of weird, a slightly weird upper bound for the length of the intersection of two of these sets. Now, if you were going to have independence, you'd have equals the product on the first product on the right. But here we just have that the measure, n is greater than m, and the measure of En intersect Em is less than or equal to the product of the measures plus the measure of one of the sets times terms of the appropriate terms of a convergent sequence. The sum of the CPs is convergent. If you have that, and if you can verify that, and it's a slightly weird looking condition, then Philip says, actually gives a very strong estimate for how many points do the hitting, not just the fact that, as I've said here, infinitely many, the set of X in En infinitely often has full measure, but the rate at which these points hit the Ens is there, given very specifically in his result. But this is all we need. So that's how we are going to get our set has full measure by using a result like that. But obviously we've got to work out how to prove an estimate of this type about pre-image sets. And at that point, a paper by Pomerenko in 1981 comes to our rescue. Seeing that year of 1981, when I looked at it yesterday, I thought Aronson's theorem was in 1978. This is 3 years later. And he does refer to Aronson. So I think he was inspired by what Aronson did, and possibly inspired by trying to understand Aronson's paper, which I find rather difficult. Okay, so what did he do? He has the assumption of contracting, which I'm not sure if I have included. Should I have included contracting? Oh, it's built into the uniform contraction. Of course, we've got uniform contraction. I didn't need to say that. Then, if you take any arc in the boundary, and you've got a family defined exactly as above, a contracting family, then the length of the preimage of E that's in that arc divided by how much preimage of E you've got is essentially like the amount, the size of A relative to 2 pi. So you get mixing going on when you go backwards. Things arrange themselves proportionate to where you're going. And the great thing about this estimate is this C to the n. It's a geometric rate of convergence. C is given by something in terms of the lambdas. So if lambda get close to 1, then obviously it gets worse. But combining these two things together is what enables us to prove the result. So those are the key things. Now, obviously, there's a deficiency here. We've got uniform contraction. And uniform contraction seems, what you would like is contraction in which the lambdas can tend to 1, but in such a way that the product of the lambdas tends to 0. That would be general contraction. So contraction with the hyperbolic distances tend to 0, but when your functions fix 0, it's equivalent to the sum of the 1 minus lambda n's is divergent, which is equivalent to the product of the lambdas tending to 0. The lambdas tending to 0, yeah. So what we would like is to be able to say, okay, here are some lambdas where the product tends to 0. Can we get a result in that case? Can we replace uniform contraction by general contraction? Yeah, that was what our conjecture was. Yeah, that we would be able to do that. Sorry. So there are 2 ways to go here, at least. And one of the ways which attracted me as a complex analyst originally was to look at Pomerenko's results and say, I don't like that uniform condition. I'm going to relax it to lambda n tending to 1. I'm going to try and prove a much better result than this, a much more general result in which I don't have C to the n, but I have something to do with the lambdas. And you can do that. But it turns out that even if you've got that, as far as we can see, you can't do better than taking, or we haven't been able to do better than what's described, well, the method that gives this result. So let me describe this result. So here we're fixing 0 again. So we're going for a shrinking target type result, but we're not saying there's uniform contraction. We're allowing the lambdas to tend to 1. And how do they tend? Well, they tend to 1. So the mu n's are the difference between lambda and 1. And we have this condition. All the secrets given away there. We have this condition. And in a way, what you would like there is the sum of in is infinity. That's what you would have liked there, that the sum of these in's is divergent. That's what we had for uniform contraction. But once the lambda n's are tending to 1, we find we have to have the mu n in there. Now, this condition, if it's satisfied, will imply that the sum of the mu n's is divergent and the sum of the in's is divergent. But there's a balance going on here in the sense that, well, I've said here, the condition implies the mu n is infinity, so Fn is contracting, and also implies that condition. But there's some sort of balance going on that if you want your mu n's to be very small, subject to being divergent, then the in's will have to have a certain size. Sorry, if you want your mu n's small, then you're not getting much contraction, so you better make your in's bigger. And that's exactly what this condition says, and vice versa, that if the in's are smaller, then the mu n's will have to be bigger. If the in's are smaller, it's a harder target to hit. You'll have to have more contraction, so your mu n's will have to be bigger, and that's the way it works with that condition. So I've written that in remark 2 here, and well, I've written more in remark 2 here, which is that if Fn is contracting at all, and this was our original conjecture, that if just take Fn contracting, well, that means the sum of the mu n's is divergent, and you can then find some INs that tend to 0, which allow which allow, I pressed no point, have I? Which allow that sum to be divergent, the sum 1 to be divergent. So if the sum of mu n's is divergent, if the sum of the mu n's is divergent, you can choose INs if you're careful, so they decrease to 0, and that sum is divergent. So in that case, Fn of zeta will hit all those targets with the INs you've just chosen, and therefore Fn of zeta will be dense in the boundary of D for almost every zeta in D. So you at least get that result out of it. And while we were doing this, Gustavo and Arthur Nicolaou were also working on these families of functions. And what they've done is define a notion of ergodicity for these functions, which I'm sure Gustavo can tell you about. But one of the consequences of their work is to get the result in the cloud as well. So that comes at you from 2 different directions. Okay, condition 1 may look a bit odd. Well, it's nice and simple. It's much simpler than the first condition we had, and it's reasonably simple. It's actually sharp that you can't improve that condition. That if you have a given mod in being infinity, then you can't take mu n's. You can't in general take mu n's that make that convergent. Yeah, if you set yourself a mu n that makes that convergent, you'll be able to produce an example where it doesn't work. So that condition is sharp. How do we prove it? I said we don't use the generalizing Pomerenke. We just arrange the functions in consecutive blocks. So you've got this sequence, little fn. The product is tending to 0. You go along, making sure the product of the derivatives is less than a half, and you haven't unnecessarily made it too long. And because of that condition 1, when you do that, it ensures that the sum of the INKs that are at the ends of those subsequences are divergent. That's the key thing. So you have a new sequence, FNK, and sums INK, and then you get hitting in that case. So you will have hitting in the original case also. Right. Okay, so I started with the ADM dichotomy, and I've been talking about shrinking targets. And the idea was that by working with shrinking targets, we'd be able to prove something about the original ADM dichotomy. And this is what we can prove. So what have we got now? The key thing that in this theorem is that that ought to have a little A on it, I think, isn't it? This is in the archive paper. We're not fixing 0 anymore. So the orbit can go to the boundary in any way it likes, or it doesn't have to go to the boundary. It can zoom about all over the place. And now previously we were, the thing that determined the contraction was the derivative of the little fn's at 0, because we were fixing 0. Now we have to look at the hyperbolic derivative, if you like, the hyperbolic distortion along the orbit, wherever the orbit is going. So we get the derivative of little n at capital Fn minus 1 of 0, and we have to multiply and divide by hyperbolic density in order to make that invariant, conformally invariant. But essentially, it's the lambda n that we had before, but just adjusted to go along with the orbit. Right, so our condition now is not that the mu n times in is divergent, but the mu n times the distance to the boundary. So we had wanted, if I dare press this button, we'd wanted to just have that term in there. But now we've got this mu n coming from the amount of contraction that we've got. Then the conclusions, you can express these conclusions in various ways. It's obviously a bit awkward because the Fn of 0 orbit can go anywhere in the disk. So just saying what the first bullet says, that Fn of zeta is dense in the boundary for almost every zeta, while that was a very strong condition when we had a Danjoy-Wolff point, now Fn of 0 could be doing that. So it's not, it wouldn't be surprising if Fn of zeta was doing that. That would be consistent with them doing the same thing if the Fn of zeros went round. But still, it's often we normalize and we say, I mean, one of the things you can do when you're not worrying about iterating an inner function, you've just got forward compositions of inner functions, is to introduce rotations and make sure your orbit goes along the positive real axis just by rotating and then unrotating and rotating and unrotating, because you're not trying to conjugate. You're just trying to get the same dynamical behavior. So, but anyway, you get Fn of zeta as dense in the boundary. But more interestingly, well, in putting it a sort of stronger statement, I think, in a way, is that Fn zeta minus Fn zero. So the set where that tends to zero as n tends to infinity has measure zero. So the behavior on the boundary relative to the internal behavior is chaotic. How do we prove this? Well, remark that condition again is sharp. We produce a counterexample that works for the previous theorem, and then we beat it to death by adjusting it into the different situations. So there's one counterexample, and then it gets applied in lots of different situations. Once you've got that first one, you know that you can do all the rest. So here's the proof idea. On the top, we've got the original f's, little f's, and then a capital Fn zooming from the first disk to those are supposed to be disks. And then there's one arc on the boundary, the red arc, which is the same arc in each case. And then we use Möbius transformations to move the orbit to zero down below. So we have an equivalent dynamics going on below with the g's, but the arcs change. And essentially, the size of the arcs down below is related to, dare I touch this again, that quantity. So the arcs below, I think, are bigger than that quantity or smaller than that quantity. I can't remember which way around it goes. But anyway, they're very closely, most of the time, they're within a constant of that quantity. And so if you are hitting a shrinking target down below with the GNs, that corresponds to the FNs hitting an arc above. And that's true for any arc. You take any arc above, no matter how short, then the GNs will hit the related shrinking target below. And the conclusion is that the FNs above have dense orbits almost everywhere. So that's the idea of the proof. And this is, in a way, where we started trying to get results of this type. And we did the transformation backwards to realize that it was all about shrinking targets. And that already went on in paper number 2, that we knew about that idea. That was when shrinking targets appeared, when we were producing examples in the second paper. Okay, well, I'm going to probably finish rather early, which apologies. Here's a summary of what we can do in terms of the ADM dichotomy, and I'll talk a little bit about where the gaps are. So A is the first theorem I mentioned, that if the sum is convergent, then on the boundary, almost everywhere, Fn zeta behaves like Fn of 0, or indeed like Fn of any z that's in the domain. Then secondly, if the sum of 1 minus Fn 0, if the distance to the boundary times this mu n is infinity, then you get, well, the function's contracting, but you also get this bad behavior on the boundary. And an obvious question is, there's a gap there between those two, and what happens in the gap? And at the moment, anything can happen in the gap, in the sense that we can produce contracting examples in which either the conclusion in A holds, or and in another example, the conclusion of B holds. And in each of these examples, the sum on the left is divergent, and the sum on the right is convergent. And so at the bottom, yeah. So the key thing is that the sum of the mu n's times the distance to the boundary is convergent. And once you've got that, in that situation, you can have either of the behaviors above going on. So the sort of conclusion from that is you can't work out what's going on the boundary just by knowing how close the orbit goes to the boundary. The functions, it's the behavior of the functions inside that can affect that. And when it comes, well, if you take this back to the shrinking targets result, the theorem we have the example we have that shows that the shrinking target result is sharp really depends on a very special way in which the shrinking target it's a nested sequence, but the way it relates to the functions themselves. And if you were to take the same shrinking target for those functions and move it to the other side of the unit disk, you would probably find that the result went the other way. There's some specific relationship between the functions and the type of shrinking target you have. So something similar is going on here. So there's something subtler about when you get one behavior rather than the other. It's not as simple as just the distance to the boundary. And so with apologies for finishing early, thank you for your attention.
Thank you, Phil. And there's plenty of time for questions and comments.
First hand was. Okay, look, Laura. Sorry. Hi.
Thank you. So I have two questions, slightly interlaced. So one question is, how does this translate back to the study of the wandering domains?
Ah, yes.
And the second question, I'll ask to you at the same time. So study of shrinking targets typically leads to study of higher order Poincare recurrence. So like the behavior of the recurrence speed, the limited distribution. Have you thought about this, or?
I'm aware from looking at the theory that's out there that this is something we probably should have done, but we haven't done it. We've just been concerned with, what happens almost everywhere in a simple terms. For the first one, yes, we are very aware of that. I guess we have some idea what's going on, that the orbits on the boundary either do similar things to the things inside or that they're completely different. Many of the examples that one looks at are lifts, and they're lifts of invariant domains for which you can easily work out, or it's already known what goes on the boundary. I think it gets a little bit harder when you get a wandering domain that there isn't a lift, and then you've got to. There's a lot will depend on how the Riemann mapping to the unit disk behaves. So you'll need to know quite a bit about the geometry of the wandering domain, and is your orbit, what's going on with the orbits as the wandering domain moves along, and are they moving towards a cusp, say, or are they moving towards, what sort of boundary point are they moving towards? And then the Riemann map will reflect that when you move it back to the disk. So yes, we're very aware that that's something we ought to be thinking about and hopefully doing something about.
Thank you.
Laura, sorry.
Oh, there's another question.
Anne.
Yeah.
Oh no, you are getting your turn.
Oh, no.
You're getting it.
Oh, thank you. Can you go back to your summary slide on the previous page? So before getting to the fancy examples of part C, so to do an example that does part B, but does not have a Danjois point, can you say a little bit about how you produce such
Which doesn't have a
examples that-
Danjois.
Yeah, that's contracting, and does not have a.
Well, you could take one that does have a Danjois wolf and just put rotations in everywhere, and
I've never done it before, so
No,
can you tell
okay.
me how to do this?
well, okay. If you take a sequence, if you take the iterative, if you take the iterates of an inner function that go along the positive real axis, and at every stage between your fn and your fn plus 1, you put in a rotation so that instead of it landing on the real axis, it lands somewhere else on the same radius. And then at the next stage, you unrotate it and put it somewhere else on the real axis, off the real axis. Then you can kind of make points.
Post-composing with
Absolutely.
a rotation to spread it around.
So you're making an equivalent sequence, but it's going all over the place instead of going along the positive real axis, which is why we often bring them back to the positive real axis, because then you have some better understanding of what's going on. It's easier to see the dichotomy because you've got this freedom. You're not conjugating. You're just doing equivalent behavior.
I see. Thank you. And then I did want to ask also what the Dini condition is, since I don't know it.
The Dini
and I'm
condition.
curious.
Yes. I hope somebody. Okay. It actually appears in a Carsten paper on quasi-conformal mapping. So phi of x over x squared dx at 0, big less than infinity. So this is for, if you're wanting to say how smooth your boundary is, then you say the boundary must lie between a pair of functions, phi and minus phi, and it must be, that must be convergent. So 5x and x to the 1 plus epsilon will do it, but it's more general than that. And phi just has to be, I mean, this is the condition that will guarantee if you've got some domain, if it's satisfied at every point, then you know that in the unit disk, we often use the Harnack inequality and that kind of thing for describing the behavior as you go to the boundary of you know, if your positive harmonic function vanishes there, then it's bound to behave like the distance to the boundary. If it vanishes there, well, if you want that condition in a general domain, then you better have that. Lipschitz wouldn't be enough. Lipschitz would allow it to behave very differently. But there's also, I mean, I think it comes out of the Dini condition in Fourier series. There's Dini-Lipschitz continuity or something, which guarantees that Fourier series converge to what, you know, what the input is, I think. Yes.
I think we're all learning. Or maybe everybody else knows about all this.
Well, I mean, it's not just that this is the Aula, but there's a statue of the guy out there. I mean, I mean, I thought it was just, you know, somebody. Actually, I should say one more thing about Dini. I looked Dini up, and Dini did these great things, and then was a politician as well, which is fascinating. But the London Mathematical Society, which is beloved of the people from our country, gives out honorary degrees. You know, a few years ago, I think. Well, I won't name any names in case I get it wrong. But Dini got one in 1901. He was made an honorary member of the London Mathematical Society. In those days, perhaps still, there were two every year, and the other one was Hilbert. Dini and Hilbert the same year, which I think is great. I felt much better than about having him in my thesis everywhere. Sorry.
There was another question. No?
When you have non-autonomous sequence of maps, you can speed up or delay the dynamics by inserting some identity maps in between, or by taking compositions of maps. And in doing that, the original sum, if it was infinite, you can make it finite, or if it was finite, you can make it infinite.
That's true.
So what happens? You may lose density, of course, when you take subsequences. But what happens with your sum with the mu ends when you speed up or delay the dynamics?
I hadn't thought about that at all. The mu ends, okay, so the mu ends will be 1. If you for the identity map, the mu ends will be 1 because the lambda. No, the other way around. The mu ends are 0. Sorry. The mu contraction. Yeah.
They're 0. Yes.
They're 0. Yeah. Sorry. The other way around.
That doesn't influence.
No.
But for taking compositions, if you want to go from infinity to finite, you should take compositions of the maps.
So it doesn't affect it. The
It
0.
doesn't affect it. So you can go from finite to infinite. So any
I
you
see.
can have
Okay.
for finite, you can have for infinite.
Right. Okay.
But
Okay.
the other way is less clear, because if you take compositions, you have a dense orbit.
Right,
You may
right.
lose density.
Yeah. I hadn't been thinking about that. It's somehow hearing your talk, that kind of thought came to me briefly, but I hadn't thought it through. Yes. Yes. Thank
Any
you.
more questions? If not, I think we should thank Phil again for his lecture and for all the answers. Second speaker this morning, Saeed Zakeri, who will be talking about lemon limbs of the cubic connectedness locus. Over to you, Saeed.
Thank you very much, and it's a great pleasure to be here again. So let me begin by recalling a classical picture in the Mandelbrot set. We have the main cardioid, the central hyperbolic component of the Mandelbrot set, and we have a bunch of primary limbs that grow out of the boundary of the main cardioid. And a basic fact in Doherty-Hubbard's theory of the Mandelbrot set is that there is a one-to-one correspondence between these limbs and rotation cycles under the angle doubling map. So for example, the so-called 1/2 limb growing out of this point is associated with the cycle 1/3, 2/3, which is a period 2 cycle, rotation number 1/2. Then this is 1/3 cycle associated to this, 1/3 limb associated to this cycle, 2/3 limb associated to this cycle, and so on. So this gives a combinatorial description of these primary limbs in the sense that if you consider a limb and the associated cycle, within this limb, if you consider the quadratic polynomial and look at the dynamical plane, the dynamic rays at angles 1/3 and 2/3 co-land. They land at the same point. And here, these three rays land together, these three rays land together, and so on. So these primary limbs can be indexed by rotation cycles under the doubling map. As soon as you go to higher degrees, this picture, you have to sort of consider a more general picture, because already in degree 3, when you go outside the central hyperbolic component of the, for example, cubic locus, you see that there are bifurcation points on the boundary whose corresponding combinatorics is not of rotation type. So one goal of this talk is to describe these primary limbs and their structure that grow out of the central hyperbolic component of the cubic connectedness locus C3. This is the analog of the Mandelbrot set that are defined by these new types of combinatorics. And it turns out that these limbs are indexed not by rotation cycles, but by periodic points of the doubling map. They could be of rotation type. They could have a higher degree of degree 2. So we'll see examples of that. And these limbs are already partially visible in the one-dimensional slice pier 1 of 0 of cubics with a super attracting fixed point. This slice was mentioned in several of the previous talks. So it plays a role in today's talk as well. So let me remind you of, so this is my specific parametrization for pier 1, 0. So it consists of all cubic maps that are normalized such that they're monic and they have a fixed critical point at the origin. So this parameter A varies over the complex plane, and the cubic polynomial P sub A has 2 marked critical points. So we want to distinguish between 2 critical points. So we're going to think of the fixed critical point at the origin as the first one. We're going to label it as omega 1. And the second one is located at minus 2a, which in the language of Pascal, we should think of it as the free critical point. And the typical picture, for example, this is a perturbation of z cubed. So both critical points are in the same basin. This is what Pascal called the adjacent type. But if you go further out, this is a typical picture where you still have the super attracting fixed point at the origin with its basin, but the second critical point is outside in one of these decorations attached to it. And of course, it could escape to infinity. So in that case, the Julia set is disconnected. So in the parameter space, so this is the one-dimensional slice pier 1, 0. This is the A plane. We have this famous lemon picture. So this is the intersection of the central hyperbolic component of the cubic connectedness locus with this slice. Everything that has an index 0 refers to this slice. So if I remove that index 0, it means I'm in C2 and I'm considering the whole cubic parameter space. So this is the central component where both critical points are in the same basin, and attached to this central component, which is called the lemon for obvious reason, we have various limbs. And these limbs are actually indexed by periodic points of the doubling map. So for example, I'll explain the relation between periodic points of the doubling map and these limbs in the next slide. But whatever it is, this is called the 0 limb. This is the 1/3 limb. This is the 2/3 limb. And then for every, on this side, as you start here and move along the boundary until you get there, you have a countable number of limbs, 1 for each rational number of odd denominator. And of course, there is a symmetry because with my parametrization, that's not the moduli space. So there is a symmetry. A goes to minus A. So there's a 180-degree rotation symmetry. we have analogous limbs on the other side, which are just rotated copies. So it suffices to consider limbs on this right half, because the left half will be just the rotation of those. So let me focus on, so let me blow up the picture of the 1/3 limb here, the next slide. So that's the bigger picture. So in what sense, I mean, why do I call this a 1/3 limb? Because if you pick a cubic in this part of the connectedness locus, it has this typical picture. You have your super attracting fixed point at the origin. It has a simply connected basin. The map is conformally conjugate to z squared on this basin. So on the boundary, the action is like angle doubling map. And you can define internal angles. So you normalize it so that the landing point of the 0 rate, this is a fixed point that has internal angle 0. And then you can parameterize all the angles on this Jordan curve in the natural way. And this parameterization is dynamical. If you pick a point here whose internal angle is t, its image has internal angle 2t, mod 1. And the second, so this is the sense in which we label this as 1/3 limb. If you take a look at the second critical point, it belongs to a decoration whose root point has internal angle 1/3. So this 1/3 here for this limb refers to the internal angle of the critical limb. And the critical limb is the decoration attached to the central Jordan disk that contains the second critical point. So you can talk about critical wake, which is this entire region, or the critical limb, which is this piece of the field Julia set. So critical wake refers to the one containing the free critical point, and the root point of that, which is on the boundary of this basin, has internal angle 1/3. So under the dynamics, this point maps to this point and then comes back to itself. It has period 2. So this entire, so the dynamics is that here it's essentially z squared, and then on each of these decorations, so there are countably many dynamical limbs attached at various points here, and each limb maps conformally to the next limb, except for this critical limb, which maps to the, so this is the critical point limb. It maps to the critical value limb, not conformally. It just maps, essentially this whole wake maps to the whole entire plane. So as you start at this angle, which turns out to be 1/4, this goes to 3/4. And then as you traverse this arc, you go like this. So it maps to this wake plus 1 full turn. So it spills over. And now the interesting thing is that here you see that the internal, so this period 2 orbit, if you look at it from inside, from the point of view of the internal angles, it's the cycle 1/3, 2/3 under the doubling map. But from the point of view of the exterior dynamics, the angles associated with this orbit are 1/4, 3/4. That's a period 2 cycle of the tripling map, angle tripling map, as well as 5, 8, 7, 8. So you could say that the orbit 1/3, 2/3 under the doubling map blows up into a pair of orbits, period 2 orbits under the angle tripling map, which are, so 1/3 blows up to 1/4 and 5, 8. They land together. And 2/3 blows up to 3/4 and 7, 8. And something else that's worth noting here is that, okay, we have a copy of the Mandelbrot set here in green. So what's the interpretation of this copy? If you're in this copy, you have a central renormalization around the first critical point, which is hybrid equivalent to z squared. Well, I lied a little bit if you stay away from this root point. And there is also a non-central renormalization of period 2 around the second critical point. So this is, I think, what I have here. So the neighborhood of this disk will map to here and then will map over itself under the second iterate. And this green region, in this green region, which is a copy of the Mandelbrot set, you have so-called non-central or peripheral renormalization of period 2. That's hybrid equivalent to some, it could be any quadratic polynomial. So there is a map from, there is a subset of this limb, which is homeomorphic to the Mandelbrot set, and you have a straightening map from this subset to the classical Mandelbrot set. Yes, Kevin. It's here. For this one, for this renormalization? It's here. Yes, it's here. It's this point. Yeah, true. So let's look at this combinatorially then. This is a way of going from angle doubling to angle tripling. In this example, we had this 2 cycle. Of course, it's a rotation cycle because it has a well-defined rotation number 1/2. So M2 is multiplication by 2 or angle doubling. And what happened in that picture is that in some sense, this cycle under M2, you blow it up into a pair of cycles under M3, which are 1/4 and 5/8 together corresponding to that. So those two are the result of blowing up 1/3, and these two are the result of blowing up 2/3. Now, you may ask, in what sense this is a blow up? So why is it associated with 1/3 and not 2/3? The difference is that it's associated with 1/3 because if you take a look at the interval corresponding to 1/3, which is this interval, it contains the fixed point 1/2. So it's a long interval under the angle tripling, whose length is, it's the unique one, whose length is bigger than 1/3. So it goes around the circle. The other one maps homeomorphically. If I wanted to blow up this cycle under the doubling based on 2/3, it would be a different pair of period 2 angles under tripling map in which the second one would be long. And being longer than 1/3 morally means you're putting the second critical point in the corresponding wake. So it depends on whether you want to put the second critical point in this wake or in this wake. So maybe I can. So in this picture, we had 1/3 and 2/3. If I blow up this cycle based on this point, I end up with what I had here. So this is 0, 1/2, which are the fixed points of the angle tripling map. So I have 1/4 and 5/8, which is the result of blowing this up. And this contains the fixed point 1/2, and the other one was 3/4 and 7/8. But if I take this point, it's the same cycle, but I choose to base it at the other point. Can you guess what it would be? I think it would be 1/8 and 1/4, and then 3/8 and 3/4. So you see, now the second interval is the long one containing the. So in this order, as you go around the circle, this is the first point, this is the second point. As you go around this circle, this is the first interval, this is the second interval. So if you preserve the picture using a semi-conjugacy, you see that now the second interval contains is the long one, contains the fixed point 1/2. So, so more generally, we can consider any periodic orbit of M2 of, say, period Q. And we always order the points in our cycle increasingly, starting from 0 then. So we label the points as you see it counterclockwise around the circle, starting at 0. And suppose that this orbit under M2 has combinatoric sigma in the symmetric group S sub Q, in the sense that the ith point in the cycle will map to, so Ti will map to T sigma I. So this is just a way of capturing the combinatorics of the orbit. For example, if you have a period 4 cycle under the doubling map, for example, this is the first, second, third, fourth. Then imagine that this maps to this maps to this maps to this, and this goes back to 1. So the combinatorics associated with this orbit would be 1, 2, 4, 3, this cycle in S4. So this describes how the orbit points map around under the doubling map. And Carsten and I studied this problem in full generality. What are the possible combinatorial types of all periodic orbits of multiplication by k for some k bigger than 2, bigger than or equal to 2? So this theorem that I'm coding here is a very special case of that theorem for degree 3. But we have a general theorem for degree for multiplication under multiplication by some k, and we count how many orbits. So we sort of characterize the possible combinatorial patterns that can occur, and we count them, and we sort of parameterize them, how to produce them. There are algorithms. In the special case, the theorem, in this case, when you're talking about angled tripling map, the theorem implies that, okay, you fix this combinatorics under the doubling, and the theorem says that there are precisely q plus 1 orbits of the M3 with this given combinatorics. So we can label them as O0 up to O sub Q. Remember, Q is the length of the cycle. And they're uniquely determined by the condition of how many points of the orbit lie between the fixed point 0 and the fixed point 1/2. So in this case, angled tripling map has 2 fixed points, 0 and 1/2. So they divide the whole circle into 2 halves, upper semicircle and lower semicircle. And depending on how many orbit points you want to put on the top or on the bottom, there is a unique answer. In degree 2, given an admissible combinatorial pattern, there's only one realization in degree 2. In degree 3, there are q plus 1 realizations. So for example, the first, the orbit O sub 0 means it's the unique orbit under M3, but that combinatorial pattern for which every orbit point is below in the bottom semicircle. O1 means there is one point on the top and the rest of them are on the bottom, and so on. Moreover, we can show that, this is easy to check, that the neighboring orbits, OK minus 1 and OK, interlace. So if OK, O sub k, you write it as x1 through xk, and O sub k minus 1 as y1 through yk, then they alternate. As you go from 0 to 1, they alternate. So you have x1, then y1, then x2, then y2, and so on. And this k, this index k, shows itself in this condition that the fixed point 1/2 lies in exactly the kth interval. So this is the sort of, when I think about it, this is the sort of mental picture that I have. I have some cycle under the doubling map, starting with of length q, starting with t1, t2, ... tq. And then I designate one of these angles, say t sub k, the kth one. It goes to T sub sigma k, depending on what your combinatoric sigma is. And then when you blow it up, there is a unique way of blowing it up into pairs of period Q points under the tripling map, so that they're neatly arranged around the circle. So T1 blows up to a pair, x1, y1, coming from different orbits, and then x2, y2, and so on, dot, dot, dot. And the kth one is the one containing is the long one, is the unique interval of length bigger than 1/3. So as you go around the circle, you see the same pattern. The combinatorial pattern is preserved. But since I want to base my blowing up at the kth point, I can arrange it so that the kth interval is the one that eventually you want to put the critical point in. So we call the pair x sub k and y sub k the simulating angles of T sub k. So every periodic angle under the doubling map has a well-defined simulating pair in this sense. Simulating because these angles mimic the combinatorial pattern of this orbit exactly. They have the same combinatorics. So this is an example, and I intentionally chose something which is not of rotation type. So this is the famous Cocopelli combinatorics. So it's a period 4 angle under the doubling. 1/5 goes to 2/5, 4/5, 3/5, back to 1/5. So in some sense, so rotation cycles, in some precise sense, have degree 1, and these have degree 2. So under the doubling map, things are either rotation type of degree 1 or of degree 2. You can't have more complicated combinatorial pictures of degree 3 or higher under the doubling map. So there are exactly 4 ways of blowing up this orbit, depending on where you base your analysis. So if you blow it up here at 1/5, that means in the first interval, I want to put my fixed point 1/2. It's this pair. And all the angles here, because I didn't want to clutter the picture more than this, everything is a multiple of 1/80 under the tripling map. So you get this pair. This is the union of O0 and O1. Then you see in this picture, the fixed point 1/2 is in the first interval. And in this picture, it's in the second interval. And in this picture, it's in the third interval. And in the last picture, it's in the fourth interval. So these are the exact 4 ways of blowing up the orbit that we started with. So there are 5 orbits under the tripling map of that combinatorics, but and then there are 4 adjacent orbits that sort of form this pattern, combinatorial pattern. And in terms of this picture, we get this combinatorial characterization of primary limbs in the slice PR10. So remember this picture in that PR10 slice. For example, this is the 1/3 limb. So my T or T sub k is 1/3. And the simulating angles for 1/3 were 1/4 and 5/8. So this is the analog of the combinatorial description of the primary limbs of the Mandelbrot set. One way of characterizing these limbs in PR10 slice is that within the limb L0 of TK, the 2 dynamic rays at angles xk and yk co-land. They land together. So this is the exact analog of what happens in the case of the Mandelbrot set. The difference is that here you allow more complicated combinatorial pictures. In the case of the Mandelbrot set, you only have rotations. Yeah, sure.
Cycle for doubling
Mhm.
So in your list of things included the Q cycles for tripling, but do you get all the possible Q cycles?
They're exactly Q plus one of them. So we know that once we fix a combinatorial pattern, they're exactly Q. So you have a Q cycle under the doubling with a certain combinatorics. It could be rotation or not. Then there are exactly Q plus one realizations of that combinatorial picture under the tripling map. But then if you pair the adjacent ones, you get Q pairs that correspond to Q ways of blowing up that picture. Yeah. Nothing is missed. Yeah. All right. Now let's go from this one-dimensional slice to the full cubic family, P sub 3, for which I choose this normal form. So it's essentially the same, except that you can now add B. And the connectedness locus will be denoted by C3. So we're going to define corresponding limbs in the full two complex dimensional parameter space. So choose some period Q angle T under the doubling map. Arrange the orbit points of length Q in increasing order. And imagine that your angle T is the kth one in this list. So T is T sub K. And take the simulating angles X sub K and Y sub K of this of T, defined previously. So inspired by what happens in the slides pair 1, 0, we define the lemon limb LT as the set of cubic polynomials with connected Julia set for which these two rays land together. They co-land. So it's a very simple combinatorial definition. So what is the first thing we should notice about this definition? I'm glad you asked. It's that it's not compact. So, and that's a sort of annoyance, major difficulty, that unlike the quadratic case, these limbs are not compact. For the simple reason that the condition of co-landing for dynamical rays is not preserved under limits. When you go in the quadratic case, everything is fine. But as you go higher degrees, starting with the cubic case, you can have, for example, this is a sequence of polynomials in the limb L0. That means the dynamic rays at angles 0 and 1/2 land together at this repelling fixed point. But this sequence is chosen carefully so that there is a pair of fixed points here that sort of, they want to choke off that 0 ray. And they eventually, in the limit, they do. And in the limit, you get a polynomial for which, okay, nothing. So the 1/2 ray is tame, but the 0 ray that has to stop here. So in the limit, they don't land together. So that's a simple example of a sequence of polynomials in the limb L0 whose limit is not in that limb. So we have to be aware of this phenomenon. So what is the dynamical picture of a typical polynomial in this lemon limb LT? It's very simple. Just the mere fact that you have this co-landing pattern allows you to define something like a Yoko's puzzle. So what happens is that you have, so we know that in this limb, these two rays at these two angles co-land at some point. And then you take the whole orbit. So you have x1, y1, rays at angle x1, y1 co-land at some point z1, then x2, y2 co-land at some point z2, and so on. Xk and yk co-land at some point zk, and you have the second critical point. Because this is long, it must, so because the length of this is more than one third, it must contain the second critical point. So you know that the second critical point is in this kth wake. And then so you have Q dynamical wakes here, and in the central region, you have your fixed not fixed. You have your first critical point. And what you do is you just take the pre-images of these wakes, of these dynamical wakes. You basically add Q more. So each wake here has 3 pre-images. One of them is in this cycle already. One of them is inside this, which we don't care for now. We ignore it. And you have an extra pre-image here. So from Q wakes, when you pull it back, you get 2 Q wakes. And this central region around the first critical point is a good candidate for defining your central renormalization. So you just, the standard procedure, you just cut it off by some equipotential. And the map from this region to its image is proper of degree 2, having a critical point at omega 1. And if the, so this I call this blue domain here U, and its image U prime. So if the orbit of the first critical point always remains in this region, then this map is quadratic like with connected field Julia set. Well, I'm cheating a little because this region is not properly contained in this region, but you do the usual trick of thickening it a little bit, which is okay because this co-landing orbit is repelling. So this is the standard process. You just thicken it a little bit. So modulo that obvious technical detail, you can think of this as an honest quadratic like map with connected Julia set. And in this case, if this condition is met, I say that my cubic is centrally renormalizable around the first critical point. And that gives me a well-defined straightening map, chi central, from the piece of the limb L sub t, which I call L central t, to the Mandelbrot set by straightening this quadratic like map. So we have our first straightening map based on the central renormalization. Of course, this is possible only if you have this condition, and there is no reason to expect that this condition, in fact, it doesn't hold throughout the limb. So this is the proper subset of the limb. And going back to the initial picture, we can think about the non-central or peripheral renormalization around the second critical point. So what you do is that you pull this back. There is a, oh, sorry, I went back. Okay. There is a sub region of this wake, which maps under the qth iterate over this. And similarly, if under this qth iterate, under the iterates of this qth iterate, if the second critical point stays in that region, you have your second non-central renormalization. So what you do is, again, in order to have something bounded, you cut it off by equipotentials, and then from this blue region to this blue region, you have a quadratic like map. If the orbit of the critical point under the qth iterate stays in the blue region, you have a quadratic like map with connected field Julia set. And you call your cubic non-centrally or peripherally renormalizable. And this defines a second straightening map, chi non-central, from another piece of the limb to the Mandelbrot set. So we have two subsets of the limb consisting of centrally renormalizable maps with its own straightening map around the first critical point, and a non-central, another piece of the limb on which we have a second straightening map around the second critical point. So we are interested in the intersection of these two, namely maps that are both centrally and peripherally renormalizable. So that's what we call n sub t, which is a proper subset of the limb. And we have a well-defined straightening map, chi, from this intersection to the product of two copies of the Mandelbrot set, which sends a cubic polynomial to its central and non-central hybrid classes in the Mandelbrot set. No, n is not compact, and that's the difficulty. Yeah, n is not compact. That's a difficulty and that one has to deal with. So one thing, before I state the main theorem, one thing that I want to mention is that in my previous picture, which was a sort of a cartoon of what's happening, I just drew it naively as if when you take these q pairs of angles, the landing points are different. Like you have a cycle of length q. That's not necessary. So if you assume z sub I is the co-landing point of the rays at angles x sub I and y sub I, so you can call this orbit. So these points are fixed under the qth iterate, but the actual period could be less than q. Could be, that can happen. So the period is a divisor of q, but it could be strictly less than q. And you can study this by, in terms of the, I mean, you can translate this problem. You can characterize when the period drops by just looking at the central renormalization and applying what you know about the Mandelbrot set. So it really depends. You can sort of characterize the condition of this supposedly period q orbit, the condition of this orbit to merge or coalesce into an orbit of lower period. You can find characterizations for when that happens in terms of the original angle t under the doubling, as well as the location of the central renormalization in the Mandelbrot set. So let me just, I don't want to spend time on that full statement, but let me just give you an example. Imagine t is the angle 1/5, period 4 under doubling. That's the Kokopelli orbit. So under the doubling map, you have this orbit. 1/5 goes to 2/5 to 4/5 to 3/5 back to 1/5. And I highlighted these two angles. Why? Because in the orbit of 1/5, and you can see this orbit, it happens that two of these orbit points are partners in the Mandelbrot set. Namely, the parameter rays outside the Mandelbrot set at angles 2/5 and 3/5 land together. This doesn't happen all the time. So in Milner's description of combinatorial description of the Mandelbrot set, this has to do with the fact that this is a satellite orbit in terms of its orbit portrait. It's satellite, not primitive. So when you take a look at the landing orbit for a polynomial in n 1/5, imagine parameter c is its central renormalization. This, instead of being period 4, it can merge into an orbit of period 2 if and only if your parameter c is in this limb of the Mandelbrot set. So if you enter, so initially you should think of the slice pier 1, 0, where the central renormalization c is 0. And then you move it in the main cardioid of the Mandelbrot set. The picture doesn't change that much. It just moves holomorphically. And then as soon as you enter another, so as soon as you exit the main cardioid and enter some other region in the Mandelbrot set, things could change. So this is the simple picture when c is 0. So this is in the pier 1, 0 slice. And you see that this orbit having the Kokopelli combinatorics has period 4. So this is the simplistic picture that I had before. But if I change the central renormalization from 0 to somebody in this limb of the Mandelbrot set, then this is the actual picture of the cubic. So you see that instead of a period 4 orbit, you have a period 2 orbit. And as a matter of fact, this pair and this pair have the common landing point, where here, so what happens is that as you move from 0 to a parameter in this limb, this landing point and this landing point merge together. And this landing point and this landing point merge together. So what you have is not this simplistic picture, but the central part is basically a quotient of it. So this can happen, and it will happen. So in this case, you can have all 4 of them landing together, simply because the Kokopelli combinatorics is not of rotation type. But for example, in the classical case of intertwining, you could, if the angle you started with is of rotation type, you can arrange things so that the orbit of length q, the landing orbit, all of them merge together and form a single fixed point. So that can happen. Okay, I just wanted to mention this possibility. How much time do I have? Half past according to, okay. So that means like less than 10 minutes? Okay, all right. So now let me state the main result. So remember, we have this periodic orbit of the doubling, angle doubling map. That was T1, T2, dot, 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 T. So Q, call C of Ti, the point on the boundary of the Mandelbrot set, which is the landing point of the external ray of the Mandelbrot set at angle Ti. So we want to remove Q parabolic parameters from the Mandelbrot set, remove those landing points, those Q parabolic parameters from the Mandelbrot set. This is what I denote by M star for removed. So it's some kind of a punctured Mandelbrot set, not quite punctured, M star T. And then in this language, M star of 0 is M minus 1/4. So we need to remove finitely many parameters from the Mandelbrot set in order for the next theorem to be true, but it's almost the copy of the Mandelbrot set. And the main theorem is that the straightening map from NT, the image of this, so it maps NT homeomorphically to this product. So that's the main theorem, which sort of shows that in the full cubic connectedness locus, if as soon as you exit the central hyperbolic component and you enter this lemon limb, initially you encounter a piece of it which is essentially homeomorphic to the product of 2 copies of the Mandelbrot set. Of course, you can keep going, and then you have other things like capture or whatever. So it's the full limb is much more complicated. All right, so there are some related results in the same spirit. I would like to mention the work of Pascal, which I should have mentioned earlier, that a lot of results that are quite often difficult in the slice PR10, or I think Milner started studying that slice, but there were several conjectural pictures, and Pascal actually provided rigorous proofs for many of them. There is this work by Hénon and Kiwi on straightening map for cubics, which is a sort of a precursor to what Pascal was. What happened? I didn't want to play Xbox. What did I press? Sorry. Thank you. I apologize. So they have a similar theory. They have a general theory for straightening maps based on like mapping schemata and more abstract language. But in the case of cubics, they have a similar result for cubics of primitive type. And our work is in some sense, the satellite type. It's the case that's not covered by the analysis. And also, this theorem includes the classical intertwining scheme for cubics that was introduced by Peter Osinski and Adam Epstein and Michel Yampolsky. So it contains, so in some sense, the intertwining surgery is a special case of our result when the combinatorics is of rotation type. And you sort of restrict your central renormalization to the P over Q limb of the Mandelbrot set. So here is just, you can go anywhere in the Mandelbrot set and you can take any combinatorics. So let me just say a word on the idea of the proof. So we have to show injectivity. We have to show that the inverse, so for obvious reasons, this straightening map is continuous. We have to show that it's one-to-one. We have to show that the inverse is also continuous. And we have to show that it's onto. So injectivity, the idea is obvious. It's a pullback argument. If you have two things with the same central and non-central hybrid classes, you can just define conformal conjugacies between central renormalizations and peripheral renormalizations and try to pull it back so as to promote the conjugacy to a conformal conjugacy eventually. The difficulty is that in this process, you're left with a subset of the Julia set, which we call the residual Julia set, the set of everything that doesn't eventually land on the union of the central and non-central field Julia sets, small field Julia sets. So you have to show, in order for this argument to work, you have to show that this has measure 0. Hénon and Kibi have a general formulation of this problem, and they address it in their paper. They have a way of dealing with it. A special case of this with some condition on the behavior of the recurrence behavior of the critical points for the associated quadratic is also outlined in the paper by Epstein and Yampolsky. But we have a sort of clean, independent proof for the general case, which is based on some hyperbolic geometry estimates. So, but it's there. So it's so this problem is settled without any condition on the behavior of the critical orbit. Now, continuity of the inverse, you want to prove that if you have a sequence of polynomials, sequence Pn in n sub t, and another polynomial p in n sub t, such that the straightening of Pn converges to the straightening of p, then Pn must converge to p. And for this, it suffices to prove that, so you take any accumulation point, say p tilde of this sequence, it's somebody in the cubic connectedness locus. It suffices to prove that this guy is in your limb. In other words, it suffices to prove that the co-landing condition persists under the taking the limit. Because if this happens, then it's very easy to show that under this condition, it actually has to be in NT. And by continuity, chi of p tilde must be chi of p. And by injectivity, they must be the same. So you prove the result. But this is not trivial. This is something that basically you have to show that parabolic degeneration, the picture that I showed you, doesn't happen under this assumption. And this is not an issue in the primitive case, because in the primitive case, this the analog of this set is compact. So you have a bijection. If you prove that it's a bijection, continuous bijection on a compact set, automatically the inverse is continuous. So you don't have to worry about it. And I believe there's something subtle going on here that we couldn't. We're not sure if it's addressed in the case of the intertwining, but then I have to double check this. But this is something that definitely deserves careful looking into. in order to show that parabolic degeneration doesn't happen, that's a problem that even in the case of intertwining, you have to deal with. That's what I'm trying to say. And surjectivity of this map, given a pair of parameters C and D and this product, so remember, you should think of C. Q sub C is your central quadratic, and Q sub D, Z squared plus D, is your peripheral quadratic. So given a pair of parameters like this, you would like to construct a cubic with the right combinatorics and the right renormalizations. And the idea here is that you start with the quadratic Q sub C. So its external map is, of course, Z squared. You want to replace that by the external map of the right cubic in the slice pier 1, 0. So maybe I can just draw a picture and then I'll stop. So you have, so this is happening. So this is piece of A in pier 1, 0. This is in that slice. That's sort of well understood. This is omega 1. So this is super attracting fixed point. And then you have other things here. Maybe this is omega 2. And then there is a pre-image of this basin. So that basin is B. There is a big pre-image of it, B prime here. And then you have all sorts of things attached. So that's that cubic by Pascal's result in this slice. We know that there is a cubic whose second renormalization is D, what we need. And the first renormalization is just 0, Z squared. On the other hand, so essentially, we want to replace the central component by Q sub T. That's the idea. And what you do is that you have some other quadratic, Q sub C, and you have this annulus around it, and you have an annulus here that you have to define carefully. And essentially, you remove this and you glue this in. And what you get is something which resembles what you need. So now you have a holomorphic map, which inside it has something which looks like a copy of Q sub C. The problem is that there is a gaping hole here on which the map is not defined. So you get a holomorphic map. It has the right central renormalization, right peripheral renormalization, but it's not defined everywhere because there is a big giant hole. The map is not defined here. And then the problem becomes, I think that's, yeah, do a very careful quasi-conformal surgery. And for that, you have to be careful. It's not like quite often in cutting and pasting, you have some freedom. Here, you have to be careful because it's not for free. Essentially, you extend the map carefully to that thing. So what you get after quasi-conformal surgery is a cubic-like quasi-regular map. And then you straighten that. The rest of it is, so you get a true cubic polynomial with the right combinatorics and the right central and non-central renormalizations. And I think I'm way over time, so I'll just leave the last slide for, in case you're interested. Yes, so some open topic. Thank you.
Thank you for a beautiful talk. We've got time for just one or two very quick questions. That's all.
So if you consider, say, parabolic slices, say pair 1, 1, and their parabolic Mandelbrot copy in this slice, so does your NT contain this this parabolic Mandelbrot set?
Yeah, something that I didn't talk about at all is, so under my assumptions, the landing orbit should be repelling. And
okay,
that's why. So I think Carsten has a clear idea how to deal with the case where the landing orbit is parabolic, and then we have to work in that. Yeah.
So you think if we add this parabolic, then it will become compact? Is that what is missing?
I'm not sure. I mean, this is definitely something that we need to look at, but I don't even know how this limb accumulates on the boundary. So I think that's the second question. It seems to be quite complicated. So I don't think it's that simple. How the limb accumulates on the boundary of the central hyperbolic component. There are various other things that can happen. Limbs are disjoint, as in the case of the Mandelbrot set, but a limb and a rotated limb can intersect. And there are it's very difficult to imagine because like we were talking about this yesterday in the Mandelbrot set, if you go out a limb, and then if you decide to go to some other limb, you have to come back to the central because there's this tree structure. But in this case, it seems that if you go out a limb, you can just come back through some other place. So there are some non-trivial intersections. We don't yet have a good understanding of exactly what happens.
Okay, thank you.
Sure.
Thank you. I think we probably should stop at that so that Carsten has some time to talk. So thank you again for a beautiful talk. Right, for our third speaker this morning, we welcome Carsten Petersen, who will be talking about not TBA, but the universal hyperbolic Mandel parameter space.
Thank you very much, and thank you very much to the organizers, especially Miriam and Nuria, for organizing this very nice event. It's a great pleasure to be here. So what I'm going to talk about sort of originally came about in discussions with Luna when we sort of made this program to prove that, well, we wanted to solve Misha's conjecture that limbs of the Mandelbrot set have satellite copies which are quasi-conformally equivalent. And then on the way, we discovered it's not always true, but we still had the hope that our proof could be remedied in the case that the periods are the same. And now we know that it's possible. And part of that program is sort of what inspired what I'm going to talk to you about today. So it's about Duardi and Hubbard's notion of polynomial-like maps, which of course you all know by heart. And nevertheless, I'm going to start from the very beginning. So you all know it by heart because it's been so successful in proving many theorems and understanding many properties. But what I'm trying to convince you today is that it also has its flaws that we should remedy, and that it has been remedied by Misha, and that we have sort of straightened Misha's picture a little bit so that we can do nice control of holomorphic motions. So let me start with the notion of a polynomial-like map. So definition, and let me just immediately write Duardi and Hubbard so not to forget them. So a polynomial-like map of degree D, at least 2, is what? It is a proper branch covering F from Riemann surface U to Riemann surface U prime, where the Riemann surfaces are isomorphic to disks, and U is a subset of U prime. So U isomorphic to U prime, isomorphic to D. And then you're saying, well, what about compactly contained? And I want to take this as a separate statement because it's really like an external hyperbolicity condition to put on your map. And I want to stress it because, as you have maybe noticed through some of the talks, there are an interesting growing interest in the case where U is not actually relatively compact in U prime. So you still can sort of have something like this, but in a non-hyperbolic setting where the domain is not compactly contained in the range. Okay. So satisfying, I call it external hyperbolicity condition, that U bar is a subset of U. Okay. And here's our favorite polynomial-like map, U prime, U, which happens to be part of the complex plane, my board here. But in the original thinking of Duardi and Hubbard, these were just Riemann surfaces. So it should be something that we can use everywhere. And part of what was discovered later is that somehow you have to get rid of this assumption of Riemann surfaces and work with domains and, well, codomain in a subset of C. But we'll get into that. So we have here KF being the filled-in Julia set, the set of points such that Fn of Z stays in U for all times. And then it's sort of a little Bourbakistic that you start defining what you mean by equivalent polynomial-like maps. So you have one here, say F1, U1 prime. You have another one, V prime, V, F, or G. And you want the notions of equivalence, which is that you have a topological conjugacy on probably a slightly reduced range, because it's in general too much to ask that it's global. So are topologically equivalent if there exists some disk W prime in a W prime subset of U prime, such that F inverse of W prime, if you call this W, and you take the restriction F from W to W prime, and you take the restriction, well, this, and you have a phi from W into, let's call into phi of W, subset of V prime, so over here. So maybe W prime is just a slightly smaller disk, maybe it's a lot smaller, we don't really know. But what we insist is that the KF is contained in W. And it's still proper degree D to 1, where D is the degree. So can I move up something here? Yes, I'm strong. And then you're asking to have a commutative diagram where it makes sense. Phi, I wrote phi there. W prime, W, phi of W, phi of W prime. And here I have G. And phi is a homeo onto image. Okay, so that's the topological conjugacy. If you say that F and G are conformally equivalent, if P can be chosen conformal, QC equivalent, if P chosen QC, and hybrid, I put that in big letters because this is the important notion. If P is globally, or QC on domain, if P is QC plus d bar phi equal 0 AE on KF. And with that, Doherty and Hubbard proved the straightening theorem. So let's call it the polynomial straightening theorem. Doherty and Hubbard, which says any polynomial-like map. And I'm going to, the hyperbolic part was just to highlight that there's an interest in non-hyperbolic situation, but I'm going to assume hyperbolicity in everything that goes. So any polynomial like f from some domain u to u prime of degree d is hybrid equivalent to some polynomial p of degree d. And p is unique up to affine conjugacy. If if KF is connected. So far, so good. We've seen this on slides in several talks. I should be able to. So we call, by definition, P is called the inner class. Of F. And once you say inner, there must also be some outer, and indeed there is also an outer class. And to define the outer class, we need to work a little more. So let me reuse some of the picture we have up here. And in order not to make my talk too long, I'm only going to define for you the external class in the case KF is connected. So here's our polynomial-like map. If KF is connected, then we have blue is maybe not the right color here. We have an annulus between U prime and KF. It has a certain modulus. So we can take any annulus surrounding the unit disk with inner boundary, the unit circle, having the same modulus. And so we have a biholomorphic map, which I will also call phi. So from U prime minus KF onto some annulus A. We have the image of the boundary of U, or even the image of U minus KF, which is a sub-annulus. I rename this to A prime, and I call this annulus A. We take the conjugate map. So here, again, I'm reusing the term G to be phi inverse F on phi from A to A prime, which is now an ordinary degree D covering, which with the property that when you tend to the unit circle, images tend to the unit circle, so you can do Schwartz reflection in the unit circle. You thus extend G to a circle covering. I write it in here from S1 to S1. Of course, there's also the reflected domain inside, but the interesting part is the map on the unit circle. But what we see here is that there's a lot of choice in G. I could change my annulus A prime and I would get a different map. So in order to this, what you do is you introduce the external class. We could call G an external map. And we take the external class to be the real analytic conjugate class of external maps. Because if you change the annulus, you easily see that it amounts to conjugating your external map by a real analytic circle map defined on some big annulus. So we take G, or external class, of F is, sorry for my, is the real analytic conjugacy class of G from S1 to S1. So we can use this liberty to easily prove that the map G is expanding on the unit circle, thus giving sort of, what do we say, justifying my use of the term hyperbolic externally. So how would you do? You just choose your outer annulus to be a round annulus. And then you get whatever you get inside. You take the hyperbolic metric on now a round annulus. I have a sub-annulus inside, which is, and I have a covering map, so it's an isometry, but the inside annulus is well inside. So the ratio of the two is bounded from below by some constant bigger than 1. And on the circle, it's constant. Well, I mean, I have the hyperbolic metric, if A prime is round, is constant. So I'm expanding with respect to this metric, and this tells us that G is in fact has a derivative which in norm everywhere is strictly bigger than some constant which is bigger than 1. Okay. So what's the problem with that? So the problem is that somewhere lurking in the background, there's the notion of renormalization. And you would like to understand renormalization as a complex analytic operator on some space. And giving these objects a structure, or the set of such objects, a structure as a complex analytic space on which you can define a renormalization as a complex analytic operator is a nightmare, if it's even possible. So one of the problems is, well, that we have this notion of conformal equivalence. So if you have two conformally equivalent polynomial-like maps, then they have the same external class. So if I were to sort of look at the fiber, because the natural thing would be to take equivalence under a conformal equivalence if you want to make a good space. But it's not clear at all that when you change from one to the other, that there's any relation between the size of, or even dimension of the space of deformations in for one polynomial-like map and another polynomial-like map. So you better forget about the general notion of conformal equivalence. It's just giving us too much. Also, you cannot really, on the other hand, you cannot really give up on that if you preserve the notion of external class as an equivalence class, because then, yeah, changing f by a conformal change would change probably at least it changes the annulus here, and so it's not good to keep also the notion of equivalence class of external maps. And somehow this was realized that this is a problem, I guess, towards the end of the 90s. I don't know if Misha was the first to realize it or Kurt was the first to realize it, but at least Misha is quoting Kurt in his now famous paper on the hairiness conjecture of Milner, as Kurt introduced the idea that instead of having polynomial-like maps defined on Riemann surfaces, we should only look at polynomial-like maps for which the codomain is a subset of C. And then we should also only consider maps to be equivalent if they are affinely equivalent, or you have a restriction of one which is equal to the other, so they're the same fill-in Julia set, or you can do a chain of such equivalences. Okay? So this is sort of a drastic reduction in what you can do. So now we are only working with polynomial-like maps in C. We have reduced the conformal equivalences to be affine and restriction, essentially. What Kurt also says that if you do this, then we can introduce a natural topology on the space of polynomial-like maps, simply asking that and maybe I should start writing something. I write Macmillan. So U prime should be a subset of C. Equivalence, conformal equivalence should be affine equivalence. Plus, and then we can have a simple restriction equivalence. So simply that, just as I did in the beginning, I said maybe we take a smaller codomain. It's pre-image, it contains the filled Julia set. It's still the same map, it's just the domain is different. And then finite chains of simple equivalence. Simple equivalences. These are a little bit a nuisance. I'll see if I can have time to talk about that, but we'll see. And then he says, let's define a convergence of polynomial-like maps. So if you have a sequence Fn from Un to Un prime, you say that this converges to some F U prime. If, say, you put 0 in here and 0 in here, sort of a marked point, then that 0 UN converges Car-Theodori to 0 U. So let me just continue here. So 0 UN converge Car-Theodori to 0 U, and Fn converges locally uniformly to F locally uniformly on U. So it turns out this defines a topology on the space of polynomial-like maps of degree D. So all is good. And this is sort of, I guess, where Misha takes over. He says, okay, let's specialize to the case of quadratic polynomial-like maps. So Misha, maybe I should say Ljubich here. But since you're in the audience, I think it's okay. D equal 2. And from now on, we're going to distinguish between a quadratic polynomial-like map and a quadratic-like map. Okay? So we have affine conjugacy. A quadratic polynomial-like map has a unique critical point. So by affine conjugacy, you can always put that at 0. So we're going to consider maps, polynomial-like maps, F U U prime, 0 in U, f of z equal to some constant plus z squared plus higher order terms. So it's enough to consider these by conformal equivalence. Did I want to say more? Yes. He abbreviates it QM, quadratic maps, quadratic-like maps. I don't have a good curly font in my hand here, so you have to live with my Roman. So if you really take this seriously, and of course he did that, then so this is a subset of C, then you do have a canonical choice of external map, because you can now define, so again, I'm going to assume KF connected, and we can talk about non-connected if we have time. We take phi from the Riemann sphere minus KF to C hat minus D bar. The Riemann map fixing infinity. And then we take G to be phi inverse composed with F composed with phi, where defined, do the Schwarz reflection, take the restriction to the unit circle, plus Schwarz reflection, plus restrict to S1. So G from S1 to S1. And now our external class will actually be an external map. There's actually one more freedom we have here that we didn't use, which is we can always post-compose with a rotation. So we can always assume that G fixes the point 1. G of 1 is 1. just conjugate by rotation. And Misha calls E the space of external maps or space of normalized external maps. And so there's a natural projection, let's call it pi, from quadratic like maps to normalized external maps. I mean, done by checking the appropriate Riemann map. Okay, so let me erase there. So we have little pi from quadratic maps to external maps, sending F to G. So I said Kurt also introduced, or maybe it's Misha, I don't really know where this equivalence, chain equivalence come from. But so we could pass to the space of these equivalence classes under simple restriction equivalence. So we introduced the space of quadratic-like germs. So these are the equivalence classes of F quadratic-like map. And so maybe I put a check here, and then this pi induces a map pi from quadratic-like germs into E. Because I mean, it's not difficult to see that when you have two that are equivalent, you get the same external map, the same circle map. So we set up a set of maps, well, quadratic-like maps. We have germified. We've set up a space of normalized external maps, and we have a projection from quadratic-like maps and also from quadratic-like germs into the space of external maps, but still there's no complex analytic structure. It should come from somewhere. So we need to see that we can put a nice complex analytic structure on the space of quadratic-like germs. So we're going to make actually both the space of quadratic-like maps and the quadratic space of quadratic-like germs into complex analytic manifolds by covering it with what Lubitsch calls covering it by Banach balls. Okay, what is that? Where can I erase everything? Okay. So if we have a domain W in C, we can consider the vector space BW of F from W to C holomorphic functions. Okay. And we can equip this with the subnorm. So we can take BW and equip it with the subnorm. And then this vector space becomes a Banach space. Now, if I have F from V or U. Yes. Yes. So holomorphic continuous on W bar. Thank you. So I should have put up here precisely for this condition. We want our polynomial quadratic-like maps to have well, domains which are Jordan disks or maybe even quasi-disks, because we want to do some quasi-conformal stuff afterwards. So maybe I should write here U prime quasi-disks. So if we start with F from U to U prime, a quadratic-like map, then of course F belongs to this space. And I can consider a ball around F for this metric. But actually what I'm going to take is not a full ball, but we're going to take codimension 2 sub-balls. So remember that F of Z is some constant plus Z squared plus higher order terms. So we are going to consider B F epsilon to be the codimension 2 subspace consisting of F hat of Z equal to some constant C hat plus Z squared plus O of Z cubed. So what I'm allowed to vary here is the constant term. The first order term should always be 0. And then it's sort of like an affine change. I'm insisting that the coefficient of Z squared is 1. So you could say I take F and then I add maps which have a constant term, and then after that starts at cubic order terms. Then it's a not too difficult exercise in with the Cauchy's theorem. Yes? What condition? Thank you. So the again continues up to the boundary. Well, I take F in this space B U. And I ask that the subnorm between F hat and F is bounded by epsilon, or is smaller than epsilon. Yes, thank you. And we call this a Banach ball. Well, not a little bit ahead of myself here. I was going to say that it's an easy exercise with Cauchy's theorem to see that when I have F U prime, maybe the critical value has already escaped, maybe not, but I can always find a Jordan disk quasi-disk slightly or so big that it contains U and X. Call this V prime. And then if I look at maps in this, so if I have F hat, so the statement is given V prime quasi-disk containing U union or U bar union critical value, so C. Then there exists an epsilon bigger than 0, such that for all F hat in this Banach ball around F and radius epsilon, if I look at F hat from the pre-image, let's call it VF hat to V prime, then it's in quadratic-like maps. Essentially, you take epsilon to be the minimum distance between, or 1/2 between boundary of V prime here and the boundary of U prime. Then you use Cauchy's theorem to see that everybody inside the closure of V prime has 2 pre-images counting multiplicity. So you have a degree 2 map here, which is then a polynomial-like map, quadratic-like map. So we can say that this injects into the space of quadratic-like maps simply by restricting to this. And it injects because if you have 2 different ones, it means they have different power series, so they are different. And then it injects into the space of quadratic-like germs. And then you need some heavy machinery from the theory of complex analytic Banach manifolds to say that this is enough to, that if you cover your space with these Banach balls, then in fact you have what we call a complex analytic Banach manifold. I'm not an expert on that, but I gather that your father was an expert on this. Ah, yes, yeah. So you would call it a complex Banach complex space. Okay. Yeah. I'm not going to write something here. Okay. You make a citation to Misha. Yes. So you may wonder why is this not an open set? Hmm? And so here. So the problem is that we can take restrictions. So if here is our fill-in Julia set KF, maybe it's connected, then I take a tiny little, or it doesn't even have to be that tiny little, but a little neighborhood, quasi-disk neighborhood, such that the pre-image gives you a restriction which is in the equivalence class. Okay, it's just a restriction. But then you can make an arbitrary small perturbation whose natural boundary of domain is just that little disk. Just to make this a quasi-circle, a fractal quasi-circle, and make, yes. So you can easily do things like that. So you can easily construct maps which are arbitrarily close in the uniform topology on a small disk to F, but which has no extension to the big ball, and so they're not in the big ball. So that's why these Banach balls they're not open sets. So it's a sort of a funny notion of complex analytic space, but it has its virtues that you can, once you're in a Banach ball, you can do everything you want. How much time do I have? Oh, 5 minutes. So we could consider H0 the hybrid class of Q0 of Z equal to Z squared, which is certainly in our space of quadratic-like maps. So, and if you look and see when you cover this H0 with Banach balls, it corresponds to making C equal to 0. So it's a codimension 1 condition. So relative to the space of quadratic-like maps and even quadratic-like germs, it's H0 is a codimension 1 submanifold, or whatever complex analytic space. Is a codimension. I'm going to write submanifold. Maybe you don't like it, but at least we have a name, and then we can redefine manifold. A codimension 1 submanifold, okay? And we could, for any C in M, we could define HC to be the hybrid class of Q sub C. And then the big structure theorem that Misha has for the space of quadratic-like germs can be written something like the following. For any C in the Mandelbrot set, HC is a codimension 1 submanifold. Okay, so it's almost everything except you have one transverse dimension. And what do you see in the transverse dimension? So if you look, take G, so and for all G in the, I'm cheating a little bit. I'm going to remedy that a little bit later. For every G in an external map, you look at the pre-image of G under this projection from quadratic-like germs to external classes. We call it CG. Is a Riemann surface isomorphic to D. So maybe I should make a kind of an illustration. So here is H0. Here is the plane corresponding to quadratic polynomials, so Q sub C plane. We have a copy of the Mandelbrot set sitting in here. This is H0. We have this projection to E. I take a G here, an external map. I look at the pre-image upstairs, and I get some kind of Riemann surface, CG. And I could define the connectedness locus, CG, like the, so this is this union over C. So union over C in M of H sub C. And if I look at CG intersected with the connectedness locus, I get something which is in fact a copy of the Mandelbrot set, which is compact subset of CG. So inside this Riemann surface, you see a copy MG. And you see all the codimension 1 Riemann manifold, codimension 1 submanifolds corresponding to each C passing through in a unique point. So maybe I should that. Can you say it again? Yeah, I only did it, but you can, Jordi and Hubbard has a construction that works for non-connected Julia sets. Yes. So let me add that for all C and M, the number of elements in CG, so also for all G and E, CFG intersected with HC has only 1 point. And so as a corollary of this, you get that all our little copies here are quasi-conformal copies of the actual Mandelbrot set. Because of this structure with Banach balls, if I have a place, then I can find a little Banach ball around it. In that I have holomorphic motions. Then I can patch my way with Banach balls to where my hybrid class connects, and then combining a lot of holomorphic motions. But it's clear that it doesn't really give you an effective bound on if you have 2 nearby copies, how much do we need? And I guess I'm over time, so I should just try to make a short statement here, which is, part of Misha's picture was that he said P from H0 to G is actually a homeomorphism. Because, I mean, you can go forth and back, and it's clearly continuous. H0 has a complex analytic structure. External maps has a real analytic structure. But we can forget about the real analytic one and give it the complex one from H0 via this homeomorphism. Okay. My point, what I want to make is forget about this space. Just stay with H0. And when you do that, then in fact, you can immerse this picture into a space which is simply H0 cross C or C hat. So each Riemann surface here, which is actually, well, you can immerse that into a copy of C in a natural way, in such a way that the mapping is complex analytic. So straightening Mises space of quadratic-like germs, you can straighten it into the product space H0 cross C. And now life is a lot easier because now you have things sitting inside C. And you have, so in the, either you have a G or you have an H here, which has a super attracting fixed point. So it's almost as good as having a circle map. I mean, after all, what we really need is the external map. So we can just compare things, instead of compare things with outside of the disk, we can compare it with the complement of the filled-in Julia set. And then using that, we can do some gluing construction, which depends holomorphically, so that you actually get nice copies of the Mandelbrot set sitting here. And the difference between two is actually, so you do a something like Luna was explaining, you choose some quasi-conformal homeomorphism, which is a hybrid equivalence between H1 and H2. This is the external class level. So you have phi hybrid from a U1 or U1 prime to U2 prime, hybrid equivalence. And it goes with the picture, but I didn't say this. So you have all the same external class in a fiber. So this you can simply lift to a holomorphic motion between, well, I should say something more. So take phi, it has a certain quasi-conformal dilatation. You take mu, and you use this to define a Beltrami disk. Okay? So from phi, you construct one parameter family of quasi-conformal homeomorphisms, which starts at U1 being the identity, and which is phi at some parameter R, which is given by the size of mu. Okay. So you take such a Beltrami path, and you can lift this to a holomorphic motion between the copies of the Mandelbrot set because you are in C. So you don't have to worry that things are crossing, because now things are straightened out and they're in the same space. So suddenly, instead of having to cover your space with balls to connect, you can simply define a Beltrami disk based on any hybrid conjugacy between the base maps, the H0 in one and H0 in the other one. And this is what was needed for Luna's case. So maybe I should say one more thing, that in general, so I said this is a universal space. So when you see, say, a one parameter family of quadratic-like maps, it's not going to be a vertical fiber. It's going to sit somehow transversely, but always when you are around some point, it's locally. So you have in a little ball, it's very close to being in the same, and you have, if you make the ball tiny, you need only epsilon amount of dilatation to go from nearby fiber to the central fiber, so that there was a essential supremum and limit r tending to 0, and this comes from, you have to modify a little bit between your family in one end and your family in the other end. So it's a little bit fast now, but okay. So I guess I'm out of time, so I should stop.
Thank you for another beautiful talk. Fantastic talks this morning. I've been very lucky as chair for the session. The others have been fantastic too. But I'm particularly pleased with this morning. One quick question from Laura. Harry, oh, what? Sorry.
Yes.
No, this very fast part at the end, you made, I just wanted to slow you down on one statement. The statement was that there was some kind of embedding of the Lyubich QG space into your straightened H naught cross C space, and you called it natural. And I was just wondering how do you define
What is natural? What does it mean?
Yeah, what did you mean by natural, and how is it?
When you think of Doherty and Hubbard's map from the complement of the Mandelbrot set to the complement of the unit disk, do you think of this as a map from the complement of the Mandelbrot set into the dynamical space of Z squared plus C? Or do you think of it into the dynamical space of the external class given by Z squared plus C? Okay. And the situation is the same here, that the way you parameterize the complement is that you just project, but normally what you project is into the space of the external class or external map. And what I'm saying here, instead of projecting it into the external map, just stay with H0. You are centered in H0. You have a quasi-disk and you have a domain. Why don't you just project your critical value into there? Because you are going to have a nice conjugacy from the outside until the level of the critical value. So you can sort of take the disk up here, and then you take the dynamical space for that. You remove the filled-in Julia set, and then you remove the Mandelbrot set up here, and you identify a point in dynamical space with the image of a critical value coming from, just as we do for the Mandelbrot set. So that in this way, you're sort of gluing two pieces of two disks to form a Riemann sphere. And then the only part here in differing from what Misha did is to prove that that construction actually is complex analytic if you just insist on working with H0. So somehow Misha's proof, I think you were a little, pardon me for saying this, but it seemed like you were a little confused when you were doing things. Because somehow you identify H0 with epsilon, and then when you want to prove that things are not complex analytic, somehow taking the real analytic structure by doing some reflections in the unit circle and saying, oh, then it cannot work because you have this reflection symmetry. Forget about it. The complex structure comes from H0.
I just would like to mention that this identification E with H0, it is kind of inspired by the Bears construction, which people know here very well. So Fuchsian groups, so space of Fuchsian groups does not have obvious complex analytic structure. So when Bears did the surgery to turn this real analytic space to complex analytic space, that's exactly what is going on here. Space of circle endomorphisms does not have natural complex analytic structure. Doing this surgery, you turn this space to H0, which has natural complex analytic structure, and you just borrow this structure from H0 to epsilon. So I think that it was Bears who was confused.
Okay, on that note, let's thank both Misha and Carsten.
Okay, so welcome to this afternoon session. It's a big pleasure to introduce Matthieu Astorg from University of Orleans, and he will speak about horn maps of semi-parabolic Hénon maps.
Thank you very much, and thank you for the organizers for giving me the opportunity to give this talk. It's a great conference, and it's a great pleasure to be here. And especially here in Pisa, so the theorem I will talk about is made in Pisa. So it's very nice to be able to talk about it here. Okay. Okay, so let me start with a quick overview of the topic of this talk. Okay. So the background, I guess, of this talk is in dimension 1. There's this classical theory parabolic implosion, which we've already heard about from Alex's talk. So if you have, let's say, a polynomial map with a parabolic fixed point at 0, and let's say that it is a simple parabolic fixed point, so the z-squared coefficient is non-zero, then you can define a Horn map. And even though I'm sure most of you know a lot about this, I will recall the construction. And this, the idea is that this Horn map describes, in some sense, or gives you information about dynamics of perturbations of this map. So if you understand the dynamics of the Horn map, if you understand the dynamics, okay. If you understand the dynamics of the Horn map, then you can say something about the dynamics of perturbations of the initial map. And then, in turn, you can transfer this to the parameter space to obtain information about the parameter space. And for example, one of the most famous results in this direction is this famous theorem by Mitsuo Shishikura that states that the Astorg dimension of the boundary of the Mandelbrot set is maximal, and this uses this kind of techniques. And we've also heard again from Alex's talk more recent applications of these ideas. So this is sort of parabolic implosion in one variable. And then in recent years, there have been some interest about extending this kind of techniques to several complex variables. And in particular, what I'm going to talk today is concerned with the Hénon maps. So these will be polynomial maps from C2 to C2 of this form. So xy goes to, let me call it p of x minus ay x. They also appeared briefly in Hans' talk. So here p will be polynomial map. And throughout the talk, I'm going to assume that A is less than 1. And then you have a dissipative Hénon map. So this complex number A is the Jacobian of the map. And the fact that it's less than 1 means that the map contracts volume. Yes, I think yes. Okay. And I will be interested in the case where there is a fixed point of this Hénon map, which in local coordinates, so not this form, but as the following local expansion. So this is in appropriate local coordinates. So in particular, you have a multiplier which is 1 and the other which is A. So you have one parabolic direction and one attracting direction. Okay, and then by the work of Bedford, Smiley, and Ueda, you can also define a Horn map in this context, and it will be a one-dimensional map. So it will be a map from some domain W in the Riemann sphere to the Riemann sphere. And again, the dynamics of this map is related to the dynamics of perturbations of the Hénon map. So kind of a similar story to the dimension 1 case, but the difference is that these maps are less well understood than one-dimensional Horn maps. And the result that I want to talk to you about today is to say that these maps still have kind of nice dynamical properties in some sense. So, okay, this is sort of the introduction, and now I would start by recalling some definitions from dimension 1. before giving the corresponding definitions for Hénon maps and then stating the results. So again, for now, let's assume that we have a polynomial map of this form. And then we have this local picture. So we can find two small disks which are petals. So one is forward invariant, the other is backwards invariant by the dynamics. So this is a fixed point. And then, as you know, we can define phi2 coordinates, which are univalent maps defined on these petals. And then, since these phi2 coordinates are really only defined up to an additive constant, we can also add like a translation here. So T sigma is a translation by vector sigma. And so these phi2 coordinates satisfy this function equation. So they conjugate the dynamics of a translation by 1. And then if you, for now, I'm not really worrying about domains of definition, but now you can look at the change between these two coordinates. So you can define the Lavance map of phi sigma as this change of coordinates. So you start, I guess, no, sorry. Yes. So you start here and then you follow this diagram in that sense. And then you can also, if you want to work maybe upstairs in these coordinates, you can look at the same change of coordinates, but in the same circular order, but starting upstairs, I mean, downstairs in this picture. So you can also look at what I'm going to call the lifted horn map. Which is T sigma composed with phi O minus 1 composed with phi iota. So same circular order, but you start upstairs. Okay. And it's not difficult to check. So H sigma, of course, is just H. So I'm just going to write it H for H0. So that's a sort of a normalization issue that I'm kind of sweeping under the rug, but you can make some choice. So really, it's enough to, for the purpose of this talk, it's enough to ask about just this map H. And it's not difficult to see that H commutes with the translation by 1. So H of Z plus 1 is H of Z plus 1. And so this map really is defined on a cylinder. This is what Alex was explaining to us. So the picture is like this. Sorry? Okay. Maybe not. No, you're right, of course. Sorry, thank you. This should be like this, and this should be phi iota. Yes, like this, I think. Thank you. I will come back to like domains of definitions in a minute, but yeah, for now this is okay. So well, let's mention domains of definition. So this is for now it's not clear what this is defined, but the picture sort of looks like this. So you have let me draw. Yeah, you have okay. So first I should say that you can extend the. So by the way, the superscript here, I or iota is for incoming. So it's like the incoming phi2 coordinate, and this one is the outgoing phi2 coordinate. And then using the functional equation, you can extend the incoming photo coordinate to the whole parabolic basin. And then it's not really a symmetrical situation, so you cannot extend the outgoing photo coordinate, but what you can extend is its inverse. And I'm going to give it a letter, so I'm going to call it this psi O, and then you can extend this to an entire map from C to C. So the picture now looks like this. You have the parabolic basin, which looks something like this. And then you have this outgoing petal. This is like a fundamental domain. And you can see maybe that you're going to have two connected components over here. And this is why the horn map H, so it's defined on psi O minus 1 of the parabolic basin, taking values in C. And this open set has at least two connected components, one for these two things. Okay. Yeah. So the picture looks sort of like this. Maybe I should keep the same color. And this picture is one periodic, because the map commutes with translation by one. And it's defined on the union of these two domains. Let me call them maybe W plus and W minus. And one contains an upper half plane and the other contains a lower half plane. And then since it commutes with translation by one, you can really quotient by Z. And then if you like, C mod Z is isomorphic to C star by the exponential map. So you can really see that as a map from the union of two domains of the Riemann sphere. And the two ends of the cylinders correspond to infinity and 0 in this picture. So the top end corresponds to 0 and the bottom end to infinity. Okay, and the map defined on this set is the horn map. So the lifted horn map is defined on it's defined on this subset of C, but it commutes with the translation by one. So you can mod out by Z, and then you get a map defined in the cylinder, which you can identify with this subset of the Riemann sphere. Okay, so this is, I wanted to take some time to recall this all these objects before explaining a little bit about the situation for Hénon maps. And I mentioned that there is a link with the dynamics of perturbation. So let me also quickly state this link. So this is a theorem proved by Lavorce. So if you have, so you have your map f of z, and let's say that you take this explicit family of perturbations. So let's say that you just add epsilon squared. Epsilon can be some complex parameter. And then you find, you choose a sequence epsilon n going to 0 such that pi over epsilon n minus n goes to a constant sigma. So this implies that it doesn't imply exactly that epsilon n is real, but tangentially it has to be real. And then the statement is that f epsilon n iterated n times goes to the Lavance map of a sigma, and this is convergence taking place on the parabolic basin. So the Lavance map is not quite the same thing as the Horn map, but it's, I mean, it's the same composition of maps in a different circular order. So if you understand the dynamics of one, you basically understand the dynamic of the other. And this is why, if you understand the dynamic of the Horn map or the lifted Horn map, you also understand the dynamics of the Lavance map, and then in turns. So there's a limit, of course. So you can lose a bit some information, but that still gives you some information about the dynamics of F epsilon L. Okay, so this is what I wanted to recall about parabolic implosion in dimension 1. And now let's move to parabolic implosion for Hénon maps, or semi-parabolic Hénon maps. And maybe before talking about parabolic implosion, let me just say a couple of things about global dynamics of these maps. So you can define, so again, let me recall the formula. So you have a map of this form. And you can, so this is a polynomial map. It's invertible. You can look at points with bounded orbit, but you can look at bounded orbit in the future or in the past. So you have two notions of filled-in Joule sets. And then you can you have at least two notions of Joule sets. In fact, there will be more, but you can look at the boundary of these two filled-in Joule sets. And okay, and then you can look at, for example, J. So J is the intersection between J plus and J minus. And up. And the picture that you should have in mind is that J plus and J minus are not bounded, but their intersection is bounded. So J is going to live in J is going to live in some polydisk over here, even though J plus and J minus needs not be, well, they are not bounded. Okay. So now let's okay, and let me just say also very quickly, we'll come back to this later, but you can also define a green function forwards and backwards green function like for polynomials in dimension 1. Okay, so plus or minus. And the filled-in Joule set is the locus for the green function is 0. Okay, so now let's assume that you have a semi-parabolic fixed point. So again, I'm going to use the same name for the Hénon map, but this is really in different local coordinates. You have Taylor expansion of this form. Again, very important, we assume that A has modulus less than 1. So if A is 1, for example, then it's a completely different story and more complicated. And we, okay. And now we have results by Ueda that state the following. So we have a map from the parabolic basin to C2 by holomorphic. Such that, so maybe I'm going to call it like this, that conjugates the dynamics to translation by 1, 0. And this is a bilomorphism. So the parabolic basin is bilomorphic to C2. And we're really going to be interested mostly in the first coordinate of this map, which conjugate the dynamics which semi-conjugates the dynamics to translation by 1, as in yes. Sorry. There's yes. Translation by 1, 0. Yes, thank you. Okay. So there's an open basin. There's an open basin of parabolic basin. So two-dimensional. In fact, biomorphic to C2. But contrary to the one-dimensional case, the situation is not symmetric between attracting and incoming and outgoing, because the map is there's one neutral direction but one attracting direction. So we have a two-dimensional incoming basin, but then we have only a one-dimensional outgoing curve. So this is for the incoming part, and then for the outgoing part, we have a map I'm going to use on purpose the same notation as before, from C to C2, injective, such that psi-O composed with, it's F composed with psi-O is of Z is psi-O of Z plus 1. So the functional equation of the inverse of the phi2 coordinate. And the image of this curve, the image of C under this this map is so it's a curve in C2, but it's not like an immersed curve. Okay, so it can accumulate on itself in a complicated way, but it's injective. This is the analog of the outgoing petal. Okay. So let me draw a very naive picture. It's difficult to draw good pictures in situ. So let's say that you have your parabolic basin that is open in situ. Here you have a fixed point 0, 0, and okay, this is not at all a good picture, but then you have this curve sigma, which sort of will intersect. So part of this curve sigma will intersect the basin, but it's not contained in the basin. So a better drawing would be to imagine that locally everything looks like dimension 1 cross a disk in which the dynamics is attracted. So you should imagine that locally near the fixed point, the basin should look like an attracting petal, dimension 1 attracting petal cross a disk, cross a vertical disk on which the dynamics is contracted by factor A. And then, yeah, I don't know how to draw it, but then you should imagine that you have like a one-dimensional attracting petal, which is sort of a graph above this horizontal line. Okay. So then you can still look at this map. Okay, so now let me make sure that I write it correctly. So I guess it's going to be this one, I hope. So this one is defined from the parabolic basin to sigma. So the Fatou coordinate here, incoming Fatou coordinate, is defined on the parabolic basin, composed with the translation, okay? And then you apply this map psi O that takes values in sigma. Okay, so it's a map defined on some open set in C2, taking values on some one-dimensional object in C2. Yes. Yeah, I mean, if you, I mean, so you have to say something. It's not, I'm not claiming that it's obvious, but so locally, the picture looks like the parabolic basin looks like a one-dimensional petal across a disk, and the curve looks like a one-dimensional outgoing petal, which is like a graph. And so you can kind of see that the intersection will look locally like in dimension 1. Yes. So this is again the L'Avance map. But it looks a bit strange to iterate this map because it's defined on some open set and taking values in some one-dimensional set. So it again, you can look at things in a different order, and you can look at this map, which is again just H plus sigma, and this one is defined on. It's defined on the preimage under this entire map C of the intersection between B and sigma, and it takes values in C. So this is some open set in C. Okay, so this is a one-dimensional map. And again, we have the picture that looks exactly like in dimension 1. We have a map that commutes, so H commutes with the translation by 1. And it's defined on the union of two domains, one which contains an upper half plane, one which contains a lower half plane. It passes to a quotient by translation by 1. And the map that you get when you quotient by 1 is called the horn map again. And it also extends to both ends of the cylinders. So that part looks exactly like in dimension 1. And then there is also a theorem due to Bedford, Smiley, and Ueda, which is the analog of a L'Avance theorem that states that if you take, so I'm not going to write the exact perturbation, but if you take an appropriate family of perturbations of your L'Avance map and you iterate n times, this will converge to the L'Avance map of a sigma on the parabolic basin B. So again, if you understand something about the dynamics of this map H, then you understand something about the dynamics of this map, L'Avance map L sigma, and then you can say something about the dynamics of perturbations of your initial Hénon map. And this is exactly the topic of the talk. So great question, thank you. So yes, I wanted to give all these definitions before coming to this, but thank you. It's so okay. Thank you for the transition. So now the thing is, for one-dimensional horn map, as you know, so I guess this is due to Lavorce and Epstein. Like in dimension 1. And when I say in dimension 1, I mean Horn maps of polynomial maps. Horn maps of polynomial maps. Are finite type maps. Which means basically that there are only there are two asymptotic values at both ends of the cylinder, but more importantly, there are only finitely many critical values. So you have, in general, you have infinitely many critical points, but they all get mapped to a finite set of critical values. And this has major consequences for the dynamics. So using this, you can prove that, let me write some of the consequences. So you have no wandering domains for these one-dimensional Horn maps. You have density of repelling cycles in the Julia set, which is a basic property that we want for all of our one-dimensional dynamical systems, I guess. And we have, for example, a Fatouchi-Shikora inequality. We also have a classification of periodic Fatou components. So basically, the dynamics of Horn maps in dimension 1 is very close to the dynamics of rational maps, even though they are transcendental maps. And in higher dimension, so for these Horn maps of semi-parabolic Hénon maps, until recently, not much was known. So there's no reason. Well, I think people are not expecting that they are finite type maps. And in fact, until our theorem, I think it was a question to know whether these maps always add more than so you always have these two fixed points at the ends of the cylinder. But aside from that, I guess it was not clear that they always add periodic points. So basically, the dynamics was not understood at all. Of course, you have this one parameter of phase. So if you choose the right parameter, you can create one fixed point just by choosing the right phase. And this is basically what Betwart, Smiley, and Weda did in their paper. But if you just take any phase, in general, you could not say much about the dynamics of this map. So now let me state our result. So I just need one more definition. So let's say let G be a holomorphic map from the domain of the Riemann sphere to itself. We say that G has the small island property if, so I'm going to write a sentence with quantifiers, but then I will draw a picture. If the following holds, so for every Z0 in C star, for every, so there exists R positive, such that for every open set U intersecting the boundary of W, there exists some open set omega compactly contained in W intersected with U, such that G from omega to the disk centered at Z naught and radius R is a conformal isomorphism. So let me draw a picture to explain what this means. Okay. No, the definition states that there exists a radius. You don't know what it is. But the point is that the radius depends only on Z naught and not on U. So your map is defined on W, then you take Z naught any point, you take any domain which intersects the boundary, and then, okay, sorry, I should say things in the right order, it's important. So you take Z naught, you haven't chosen yet U, then the property gives you a disk, gives you a radius around Z naught, which does not depend on U, such that if you take any U, you will be able to find some small open set omega here, which is mapped univalently to the disk. Okay. Okay, because this is a reference to theorem by Alfors, the Alfors 5-element theorem, which states a similar kind of property, but you can take any Jordan domain. And here we say that there exists like a disk. If you take a radius small enough, there exists a disk. Yeah. So yeah. So yeah, this terminology. So we made up this terminology, but I don't think. I mean, if anyone knows if this has a name, yeah. And then the theorem is that all maps of semi-parabolic Hénon maps have this property. Okay, so here we take Z naught in C star, and this excludes 0 and infinity, which corresponds to the ends of the cylinder. Okay, so this does not work for the ends of the cylinder. And let me state a couple of consequences. So the first consequence is that the Julia set of a Horn map is the closure of the repelling cycles. Sorry. It's R. There are no N. No. Okay, so a corollary is that the Julia set is the closure of the repelling cycle. So I'm not going to define precisely the Julia set. So it's the non-normality locus, except that you need to take into account the fact that it's a partial map. So you want to say that when you're, for example, if you're in the boundary of the domain, by definition, you're in the Julia set. So this, in particular, it implies that the boundary of the Julia set can be accumulated by repelling cycles. And this is very easy to see in the case of the boundary, because you take, so you take a point Z naught on the boundary. Okay, so then the property gives you radius R, and then you take for your choice of set U, you take this this disk, and then you find a small island omega, which is mapped conformally to the disk, but omega is compactly contained in the disk. So then you have a fixed point. And you can do this for any smaller radius. Okay, so and once you have this for the boundary, then you can sort of argue that iterated preimages of the boundary are dense in the Julia set, and then this is how you get it. And another consequence is the following. So now we need to make a second assumption. So assume that the Jacobian, so the Jacobian of the map F, which is this number A, is less than 1 over d squared. So this is called substantially dissipative. Then there exists a sequence f epsilon n, which goes to f epsilon to f. So this is a sequence of perturbations of Hénon maps, such that the Hausdorff dimension of J plus of these perturbations goes to 4. 4, which is the maximal Hausdorff dimension because we're in C2. And so the way that this extra assumption comes into play is that this, so using a result by Michel Lubitsch and Romain Jardin, using this assumption, we know that there is at least one critical point. So we just need to know that there is at least one critical point. And then if you have one critical point, you can use Macmillan's result on the universality of the Mandelbrot set, and Shishikura's result on the construction of IFS with large Hausdorff dimension, and transfer this to this kind of maps. So maybe I would say no. No, the degree is the same, but the Jacobian, I guess, changes a little bit. Yes. Okay. So I guess I still have what, five minutes. Okay. So then in those 5 minutes, I want to give some ideas of the proof of the main theorem. And the proof uses pluripotential theory and ergodic theory. So I will need to say some words about currents. So recall that we have these green functions, g plus and g minus. So you can take the DDC of these green functions, and in dimension 1, if you take the green function and you take the Laplacian of the green function, you get the unique measure of maximal entropy. And this is a higher dimensional analog of this. And so if you don't know, if you're not familiar with currents, you can just think of this object as generalized differential forms. So you can think of distributions as generalized functions, and you can think of currents as generalized differential forms. So these are 1, positive closed currents. And the support of these objects are exactly these forward and backward Julia sets, J plus and J minus. And if you take T plus wedge T minus, so if you pretend that these are actual differential forms, like 2 differential forms, you take the wedge product, you get a volume form, but it's in the sense of distribution, so you get a positive measure. And this is the unique measure of maximal entropy. It's an ergodic measure. It is a hyperbolic of saddle type. So in dimension 1 for polynomial maps, the measure of maximal entropy is supported in Julia set, so it's repelling. And here, it's repelling in one direction, attracting in the other direction. So it has one positive Lyapunov exponent, one negative Lyapunov exponent. And this is what I needed to say. And now let me go back to our problem of horn maps and translate this back into the dynamics of the Hénon map. So what we must do is the following. So we pick this point Z naught, this arbitrary point Z naught, and we pick this set U, okay, which intersects the boundary. And what we must do, at least part of what we must do, like an easier, a first step, I guess, is to find a point in this open set U which maps to this point. I mean, that's the least that we can do, the first step, okay? So we must find a point here which maps here. And if we translate this back into phi2 coordinates and the initial Hénon map, if you look at the definitions of the phi2 coordinates and so on, and the horn map, you will see that this comes to the following question. So you look at your curve sigma. Here you have the image under this phi2 parameterization of your disk, okay? So it's like a small disk in sigma which intersects the boundary of the parabolic basin. And here, somewhere here, you have, let me use a color. You have a curve which corresponds to the equation phi iota is equal to, so let me call this point W0, for example. Then here you have a complex curve given by the equation phi iota is equal to W0, okay? And what you must do is you need to say that this curve will eventually intersect this disk here. So actually, you have a little bit more freedom because this is really mod Z. So you can translate this by integer. You can also translate this by integer. So really, you're allowed to iterate this disk, and you're allowed to pull back this line over here. So what you must do really is to say that if you push forward this disk, and you're allowed to pull back this line, then somewhere you will find some, let's say, transverse intersections. You must say something more, but this is basically the idea. And the idea here is to use equidistribution results to say that, so I'm going to go a bit fast here. If you take the current of integration along, so let's call this disk here D, this is going to converge to T minus in the sense of currents. And if you take so if you take this line and you truncate, so let me call this C. So you pull back, take the integration current. This is going to converge to T plus. And these two things look similar, but here we use two different results. So this is done using a theorem by Bedford and Smiley. And this is done using a theorem by Dean and Sibony. And then you can use ideas from, I'm just going to write the names, using ideas from the paper by Bedford, Lubitsch, and Smiley. And Pessin theory, we can prove that these two things imply that you get some transverse intersections between this and this, which is enough. And I think I will stop here. Thank you.
Thank you very much, Matthieu. And time for some questions.
In your Hausdorff dimension, corollary 2,
Yes.
do you need to go to a second level of horn map?
No. So we're we're just using Shishikura's result as a black box. So we are not like redoing things.
Okay.
Yes.
Thank you.
So one question, the results of Weda, Smiley, and Medford.
Yes.
So do they use the fact that they're working with Hénon map, or is just a normal form?
Yes.
Which is important?
Yes.
Yes.
You use global properties. Yes.
Any more questions?
Do you think it would be interesting, and if so, do you think there's any hope to see if this map satisfies the actual alpha silence property?
Yes. So I guess we kind of think that it does, but this was somehow enough for the consequences that we have in mind. But yeah, I wouldn't like make any definitive claim, but I think it probably does satisfy the alpha silent property. Yes.
Thanks.
Any more questions? So then let's thank Matthieu again.
Okay.
It's a pleasure to introduce Rohini Ramadas from University of Warwick, and she will talk about the tropical moduli space.
Thank you. Thank you to the organizers for organizing this really nice workshop and for inviting me. I've been having a really nice time here. Okay, so my talk is based on a recent preprint, and I very much welcome feedback on this. Okay, and it is also going to be fairly transparently related to Mitsu's talk earlier this week, and maybe slightly less transparently related to Charles' talk. Okay, so I'm going to start. I want to talk about a connection between tropical geometry and Thurston's theorem characterizing PCF rational maps. And I want to start off with an introduction to tropical geometry, essentially through examples. So tropical geometry, roughly speaking, is a way of taking some kind of situation in algebraic geometry and extracting some information from it and encoding that combinatorially via piecewise linear geometry. And the information that one extracts is usually something about exponents. And we will see this in our example. So it's a way of going from algebraic geometry to piecewise linear geometry via extracting some kind of information about exponents. So let me just dive into my first example. Well, okay, my first set of examples is going to be based on the scenario where we have U open in X, and X minus U is nice. And really nice means here it looks like a union of coordinate hyperplanes in CN. Varieties, algebraic varieties. Thank you. Sorry. So X minus U looks nice enough. It looks like a union of coordinate hyperplanes. And from this, I can tropicalize and get an object that is going to look like a union of cones glued together along faces. So let me just go with examples. So here's my first example of this is that I have C star squared sitting inside C squared. So here the complement is literally the union of coordinate hyperplanes. And the tropical picture is going to look like the non-negative quadrant in R2, where this ray over here kind of encodes or stands for the x-axis minus the origin. This ray stands for the y-axis minus origin. This two-dimensional face here stands for the origin in C2, and this cone point stands for C star squared. So we see there's some kind of dimension reversing thing going on here, but the combinatorics of this cone tells you how the coordinate axes sit together in C squared. Oh, wow, okay. This is non-trivial. Sorry. I'll try not to have that happen. Okay, so continuing with this example, let's say I have a map from C squared to C squared, F, given by x comma y, maps to x squared y, x cubed. And so let's notice that because this is a monomial map, it completely preserves this like stratification. And it preserves the C star squared sitting inside the C squared. And the tropicalization of this map, which I'll just denote F trop, is the matrix, and I hope I don't get the transpose instead, 2, 1, 3, 0, encoding the exponents of the monomial map. Okay. So example 2 is still going to be of the form U open in X, but now I'm going to introduce kind of the main character of this talk. So let's have P be a finite set, little p1 through little pn, where n is at least 3. So given this, fixing this finite set, there is a moduli space of configurations of points on the Riemann sphere marked by this finite set. So this is the space of injections from P into P1 up to Mobius equivalence, simultaneous Mobius translation. And this is a non-compact algebraic variety of dimension size of P minus 3. And I'm not going to at all describe this, but okay, it's non-compact. It has a range of nice compactifications. And in some sense, from the moduli theoretic perspective, the nicest one is denoted as MP bar and is the Deligne-Mumford compactification. So I'm not going to describe it, but I will say that it is nice enough that I get a tropicalization, which is denoted as MP trop. So this is going to be a bunch of cones glued together. Let me again just do it by example. So example 1, I guess 2.1, or I'm just not going to number this correctly. If I set n equals 4, then concretely MP is isomorphic to P1, remove 3 points. And MP bar, concretely, is isomorphic to P1 with those 3 points put back in. And the corresponding tropical picture MP trop is a union of 3 rays, 1 for each point in MP bar that was missing in MP. Okay, so now let me have n equals 5. Here, MP is complex 2-dimensional, and the cones that I get are 2-dimensional, and I'm going to glue them together. It's hard to describe this. So I'm going to first describe the local picture and then the global picture. So locally, in fact, what I see is the cone over this. So here's MP trop for P size of P4, if I take the cone over this, it's like 3 pieces of paper glued together like this. So that's the local picture of MP trop. And globally, so then, you know, I have to glue a bunch of things that look like this together, again, along these one-dimensional faces. And what I get is the cone over the Petersen graph. So this graph, which has 10 vertices and 15 edges, which we notice is trivalent. So every vertex here corresponds to a ray in this picture. Okay, so we've done a bunch of examples of the form U open in X, and we get a tropicalization that is supposed to sort of describe X take away U. And let's notice a bunch of common features. It's built up of cones glued along faces, but it's glued in such a way that the end result is also a cone. So there's always a cone point. So that this is the cone point here, this is the cone point here. You can't see the cone point in this picture because we're taking the cone over it. So we always have, in these examples, a cone point. And we have, because it's a cone, we have a scaling action by the non-negative reals. So, you know, I scale along this ray, along this ray, along this ray. Over here, in this picture, the scaling goes out of the blackboard, etc. So we have an action of r greater than 0. And I will just use the word ray to mean a non-cone point orbit of this scaling action. Okay, so now I'm going to do a second type of example of tropicalization, and it's going to look kind of qualitatively different, but it is also going to be concretely related. Okay, so for the second type of example, I want to think that I have a moving point of MP. I have a point in MP and it's moving with T. T is like a holomorphic parameter. And in other words, I have a moving configuration of points on P1. So moving point of MP, I can encode this as follows, as a tuple P1 of T, Pn of T, where these PIs are the functions that tell me how my point is moving with T. So each of the PIs is supposed to be a moving point on P1. In other words, PI, well, it's either an element of the Laurent series ring, or it could be infinity, which just means that if PI is infinity, it's saying the ith point is just staying constantly at infinity for all T. So if I have such an object, I can tropicalize it again. And what I get is called a genus 0 P marked tropical curve. This is just the terminology. But what it is it's a metric tree with ends labeled by P. So here is what an example might look like. Here n is equal to 5. So I have these infinite ends, and this tree has finite edges. Each of these finite edges has some length. So L1, L2 are the lengths. And if I tropicalized an object like this, then these lengths would always be integers. But in general, the lengths are sort of allowed to be positive real numbers. So let me again do an example of this construction. So example, P1 of t is infinity. The first point is constantly infinity. P2 of t is 0. The second point is constantly 0. P3 of t is constant 1. And P4 of t is moving with t. And let's say it's t to the k, where k is positive. So in this case, the tropical picture is going to look like this. So I get a tree that looks like this. P2 and P4 are together, reflecting the fact that the t equals 0 limit takes P4. The t equals 0 limit of P4 is going to equal 0, which is the same as P2. So that's captured by the combinatorics of this tree. And the metric of this tree, the fact that this edge has length k, is capturing the kind of speed of collision of P4 with P2. The faster it goes to 0, the longer the edge length is going to be. Questions? And let me note the distinction from all of the previous examples. An object like this does not have a cone point, and it does not have a scaling action. So there's something slightly qualitatively different. I keep trying to move the wrong thing. So fixing P, one can consider the space of all P-marked tropical curves. And a tropical curve is kind of specified by the combinatorial type together with the edge lengths. Once I specify a combinatorial type, varying the edge length is going to give me a cone. So what I would get is a bunch of cones glued together, cones for every combinatorial type. And in fact, what you get is equal to MP trop as I described it earlier, the thing that you get that describes the boundary combinatorics of MP bar. And so I should cite some people here. There's Bilera Holmes Voetman first studied the space of P-marked tropical curves as a space of phylogenetic trees. And then Speyer and Sternfels, McKelkin, and maybe this sort of identification between the space of tropical curves and the tropicalization of moduli space is really due to Abramovich, Caparaso, and Payne. Okay, so but this is like, you know, we saw MP trop from two perspectives. From one perspective, it's describing boundary combinatorics. From another perspective, it's a space of trees. And like roughly speaking, one should think of it as a space of ways of going to infinity in MP. That's what it really represents. Okay, so that was my introduction to tropical geometry. And let me sort of move closer to the actual topic of this talk. So before we've had the finite set P as this abstract finite set. Now I'm going to say P is a subset of an oriented two-sphere. And, you know, fixing this, we have a Teichmuller space parametrizing complex structures on this sphere relative to P. So roughly speaking, this is the space of homeomorphisms from S2 to P1 up to some isotopy equivalence where the equivalence depends on P. And what we get here is a finite dimensional complex manifold, but it's not algebraic. It is also, let me maybe start a diagram here. It is also the universal cover of moduli space, the space that we just saw. And this map is infinite degree. Yeah. Yeah. These maps, these are orientation preserving homeomorphisms. The equivalence is up to post-composition by Mobius transformation and isotopy relative to the mark set P, which is not allowed. They're supposed to fix the points P for all time. No, point-wise for all time. Yeah. Yeah. Okay. Yeah, so here, if we've put P in the sphere, we have a type-Mueller space, which is related in the following way to moduli space. And now, the object of Thurston's theorem is we have a PCF branched covering from the sphere to itself, and P is its post-critical set. So phi is going to be a PCF, meaning post-critically finite, branched covering. So it's not a rational map, it's just a topological object, but you can still define what it means to be PCF just by following critical points along. Orientation preserving, I'm not going to write that if it's okay. Post-critical set P. So fixing such a branched covering, Thurston defined a holomorphic pullback map on type-Mueller space. So I'm going to call it TP for Thurston pullback. And this is a holomorphic map from type-Mueller space to itself. And the dynamics of this map on type-Mueller space tell you whether or not phi can be realized as a PCF rational map. Specifically, a fixed point of the Thurston pullback map, if one does some translation, is the same data as a PCF rational map that is dynamically equivalent in a suitable sense. It's called combinatorial equivalence. Combinatorially, I'm not going to define this, but you should think of it as dynamically equivalent as opposed to a different new kind of equivalence that we'll see soon to our original branch covering phi. So if this pullback map has a fixed point, then our original branch cover is dynamically equivalent to a rational map. So we can upgrade it from topological to holomorphic. And the theorem, Thurston, I guess, and like written by Duardi and Hubbard, is that with certain constraints on phi that I won't say, so I have to exclude some branch covers covering phi, we have a dichotomy. Either the pullback map has a unique fixed point, which is attracting, or the pullback map has no fixed point And phi has a topological obstruction of a certain type that called a Thurston obstruction. And I will just say a little bit more about what these look like slightly later in the talk. Questions? Okay, so given this like topological dynamical system, we've gotten out of it this holomorphic dynamical system on Teichmüller space, which is not algebraic. And from this, Sarah Cook constructed what is known as the moduli space correspondence, which I'll denote MC for moduli correspondence. Which is a multi-valued map on moduli space. Okay, so let me just say a little bit of what we might expect. Okay, so we have an actual self-map of Teichmüller space, and we have this infinite to one cover from Teichmüller space to moduli space. And one can try to extract out of this, you know, some kind of semi-conjugacy with a map on moduli space. And this basically never exists. But you get the next best thing, which is that you get a 1 to finitely many points multi-valued map, and your model should be like the square root map, which sends a point to its pair of complex roots. And more specifically, you get a diagram like this. So this is an algebraic variety, H phi, which depends on phi, together with a pair of maps like this, where this is a covering map. This is just any old holomorphic, it's an algebraic map, and a covering map like this, so that the diagram commutes. And the correspondence is this multi-valued map that you get in this direction. Given a point here, it has finitely many pre-images here, and I like map them down to all of their image points here. So MC is you first take pi1 inverse, and then you do pi2. And that sends 1 point to several. Okay. And, you know, fixed points of the pullback map are PCF rational maps. That continues to be true for fixed points of the moduli space correspondence. Of course, I need to say, what do I mean by a fixed point of a correspondence? So a fixed point of the moduli correspondence, by definition, is going to be a point in here that maps to the same point in moduli space under the pair of maps. So that means if I took this point in here, the image point in here, well, it has multiple images, but one of those images is itself. So it's kind of a weakly fixed point. So this is F in this space H such that pi1 equals pi2 on this point. And this is equivalent, a fixed point of the correspondence is equivalent still to a PCF rational map. But it still has some kind of relationship to the original branch cover that we started off with, but it's not quite dynamically. It doesn't share dynamics necessarily with phi. It's kind of non-dynamically equivalent to phi. I will not explain that, but I'll call it, it's called Hurwitz equivalence. So Hurwitz / non-dynamically equivalent to phi. And kind of essentially by Thurston's theorem, the moduli space correspondence has isolated fixed points under the same constraints on phi. So, right, so fixed points still have a meaning. but there might be multiple. There's no longer this uniqueness of the fixed point. But also kind of the local dynamics of this moduli space correspondence mirror the local dynamics of the pullback map. Meaning if I have a tiny neighborhood over here and I look at, if I fix one inverse branch of pi1, so I'm taking like one single valued branch of the correspondence, then I can canonically I can identify that, I think, isometrically with like a little open set here mapping to its image. And in this diagram, we have kind of what's going on up here is all non-algebraic, and what's going on down here is all algebraic. So historically, actually, algebraic geometers were independently studying diagrams like this from a completely non-dynamical perspective. And not just in genus 0. In fact, they were not really interested in genus 0. The interesting case was sort of higher genus versions of this diagram. So this space H is really a Hurwitz space parametrizing branched covers. I mean, it could parametrize branch covers of higher genus Riemann surfaces, and you would get a diagram like this, where the moduli spaces here are moduli spaces of higher genus Riemann surfaces. And the diagrams like these were kind of important in the 80s for example, classifying the birational type of the moduli space of genus G Riemann surfaces. But, you know, this connection that Sarah found between diagrams like this and the Thurston pullback map sort of made it relevant to study their dynamics. They're only dynamically relevant in genus 0. So this is the only, but it made it relevant to study their dynamics. And in my thesis and a little bit beyond, I did some stuff about the algebraic dynamics of the moduli space correspondence. Okay, so now let's sort of slowly transition to tropical geometry. So as I said, you know, this diagram has been interesting to algebraic geometers for a while, and it was tropicalized. I told you there's a, you know, MP has a tropical version, MP trop. There's also a tropical space here constructed by Cavalieri, Markvig, Ranganathan. So I can draw a diagram. I'm not gonna explain this at all, but there's a tropical space here. It's again a bunch of cones glued together. And I can tropicalize these pairs of maps, and these are gonna look like, you know, integer matrices, cone by cone. So this, you know, has some meaning. And in the genus 0 case, it ought to reflect something about the dynamics near infinity of the algebraic moduli space correspondence. Because as said, like MP trop should be thought of as a space of ways of going to infinity. And so this ought to be encoding like, how do you act on the space of ways of going to infinity? If I'm going to infinity in one way and then I do the moduli space correspondence, what's happening to me? Okay, so there's a tropical version of the lower part of this diagram. Let's talk about the upper part of the diagram. Oh yeah. It's always the Deligne-Mumford compactification. It's always the Deligne-Mumford compactification. Yeah. 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 Okay. So I said, okay, either the pullback map has a unique fixed point or the branch covering has what is called a Thurston obstruction. I want to now say a little bit more about what is a Thurston obstruction. So like towards that is So back in non-algebraic land, a multi-curve on the sphere minus this finite set is a collection of simple closed curves that are all, away from the finite set. They are pairwise disjoint, and some other like a couple of other conditions that I'm not going to say. They're like essential and non-peripheral for people that this makes sense to. So here's a simple closed curve gamma 1 and gamma 2. So this pair of curves is a multi-curve on S2 minus B. And a weighted multi-curve is a multi-curve together with a choice of positive real weight for each curve. So weighted multi-curve looks like some alpha I, gamma I, where the gamma i's together are pairwise disjoint, and this is necessarily going to mean that there's only finitely many of them, and the alpha i's are any any positive numbers, real numbers. Okay, so that's a real weighted multi-curve. So now let's think about like the space of weighted multi-curves. And this is going to be like up to homotopy. So this, again, is kind of built out of positive cones because, if I fix my multi-curve, then the space of weights for it is a cone. And there's kind of gluing along faces that goes with containment of multi-curves. So it looks really tropical. It's made of cones glued along faces. By the way, I should say I'm allowing the empty multi-curve. So like the empty multi-curve is allowed, and that's the kind of cone point of this space of weighted multi-curves. And this is completely non-standard, but in my opinion, in a meaningful way, this is like the tropical Teichmuller space. And I can sort of like, after the talk, if people are interested in grilling me, I can give some like reasons, some more concrete reasons for why I think this. Okay, so Thurston gave a piecewise linear pullback map on the space of weighted multi-curves. So cone by cone, it's linear. And they glue together to give you this piecewise linear map. And an invariant multi-curve, this is like slightly non-standard, but experts, please let me have this, is a multi-curve gamma such that its pullback is a multiple of itself, lambda gamma times gamma. And an invariant multi-curve is an obstruction, is a Thurston obstruction, if this factor gamma is at least 1. So that is an obstruction. It's a multi-curve that's invariant under this pullback that I haven't told you how it works, and the scaling factor is at least 1. Okay. Now, there is actually a very concrete relationship between the space of weighted multi-curves and the moduli space of the MP trop. And essentially there's a map like this. It's piecewise linear, linear on cones. It's not a universal cover, but it's infinite to 1. What else can I say about it? Oh yeah, it is a quotient by the mapping class group, by the action of the mapping class group, as is this universal cover. So the mapping class group acts here, and it acts here, and both of these maps are the quotient by the mapping class group action. So this looks a lot like what we have here. And the first proposition from my preprint is that there is a map here that like makes the diagram commute. So let me. So one, there exists a map from weighted multi-curves to HV trop, and the diagram commutes. And this is also sort of it's piecewise linear. Tropically, it's kind of like a covering map. And what this tells you is that there's an explicit relationship between the dynamics of the tropical moduli space correspondence and Thurston's action on weighted multi-curves. And, you know, sort of everything that is, at least all of the things that I said about the relationship between the standard moduli space correspondence and the standard pullback map have analogs in the tropical land. So you can talk about a local single valued branch of the tropical moduli space correspondence. Similarly, as you can talk about a local single valued branch of the moduli space correspondence. And this local single valued branch is going to look like, you know, up to change of coordinates is a branch of Thurston's pullback map on weighted multi-curves. So local branch of the tropical moduli space correspondence, let me give it a name. So MC phi trop is the tropical moduli space correspondence. So, you know, defined just as with the moduli space correspondence, and local branches of this are identifiable. I think that's my timer. I'm out of time. Okay, let me just finish the, oh, okay, thanks. Okay. So these are given by these Thurston pullback matrices. And finally, we can talk about like fixed points of the tropical moduli space correspondence. So really we should think about this as like fixed rays. So again, a kind of weakly fixed point. So first, let me say what this is. It's the same as before. It's a point in H trop that has the same image under the pair of maps, or like whose image under the pair of maps is off by a scaling factor. So by definition, this is R in H trop such that pi 2 trop of R is some scaling factor lambda times pi 1 trop of R. And these, so I mean, that's just what it is by definition. And these can be translated into invariant multi-curves. Now, not necessarily for the original branch cover, but for some branch cover that's Hurwitz as in non-dynamically equivalent. For B prime, Hurwitz, topologically non-dynamically equivalent to our original branch cover. And the scaling factor R given for this ray is the same as the scaling factor for the invariant multi-curve. So if I have a fixed ray here, I can get out of it an invariant multi-curve gamma for some branch cover Hurwitz equivalent to the original one, and such that the scaling factor of the multi-curve is equal to the scaling factor of the ray. So putting this together, array of the tropical moduli space correspondence that is scaled by a factor of at least 1 is the same thing as an obstruction for some Hurwitz equivalent branch cover. Okay, so let me stop there and thank you all for listening.
Thank you very much. Are there any questions?
Thank you for a great talk. I was wondering, like, in the sense of this diagram, sometimes we are lucky and like pi2 is just injective and we have an actual G map on the moduli space. So does the same thing happen in the tropical version?
Yeah. Okay. So Charles and I have been working with some examples, and in those examples, what happens is pi2 trop takes some cones of the tropical Hurwitz space and maps them sort of isomorphically to the cones in the tropical moduli space and contracts the other cones. There are a lot of contracted cones. So it's not exactly that it's single valued, but there's a lot of like contracted cones, I guess. And there's like a core that's mapped 1-to-1.
But is it just like in some examples, so you can say that if here pi2
is generically 1-to-1, then I think you should be able to detect it tropically. Yes.
Oh, well, great.
I haven't, yeah. I mean, it would sort of be saying, can you detect this near infinity? Like, can you detect this at infinity at the boundary of the Deligne-Mumford compactification? And I don't think, it's not like completely clear to me that you always can, but I suspect that you should be able to.
Thank you.
Thanks for your talk. Just a plug for the analysis of this area, a tiny little cartoon picture that describes this critically finite branch cover phi determines this holomorphic correspondence on moduli space, which may be very high dimensional. But as soon as there are 5 points, the moduli space is too complex dimensional, and this gets very complicated very quickly. But it's now a dynamical system on a moduli space of complex dynamical systems, which is, I think, very much in the theme of the conference. Do you have any way of connecting the dynamics on the interior of moduli space with the dynamics on the boundary? For example, in this famous case that Sarah analyzed of the rabbit, the fixed point of TP phi for the rabbit at the center of the disk is joined to a 3-cycle on the boundary at infinity of Teichmuller space, corresponding to 3 curves that are permuted. Those curves live in your space. Is there any way to, in greater generality, find that phenomena in this tropical
When you say
world?
connected to what?
They're literally connected by analytic arcs in the Teichmuller space is one-dimensional, and they're literally connected by analytic arcs in the disk, which are then moved around. You prove that using this G map that exists.
I see.
In that case, but I don't know how to do that when you have a correspondence.
So yeah, okay. So definitely the dream is to be able to go back and forth very explicitly between the dynamics of this, the dynamics of this, the original branch cover phi, the dynamics of, you know, the tropical correspondence and, you know, the weighted multi-curves. And okay, so the tropical correspondence is like a very kind of new thing, and Charles and I are just starting to look at what the dynamics there might, like the tropical dynamics might tell you about the dynamics on the interior of MP. So one thing that, at least in examples, it tells you is you know, there are these algebraic dynamical invariants called dynamical degrees. And in like a couple of examples, you can see the dynamical degree of the correspondence by the action, the tropical action, as in there's something that is like an equilibrium measure that gets scaled by the dynamical degree. So that's like that's an example, but yeah.
Okay, so let's thank Rohini again. So we proceed with the final talk of today, and it's a pleasure to introduce Gustavo Rodriguez Ferreira from the Centre de Recerca Matemàtica in Barcelona, who will talk about universal natural families.
Thanks, Nuria, and thanks for the organizers to give me and all of us the opportunity to be here and talk about all of these very nice things. Before I start, I want to point out that this is joint work with Sebastian Van Strien from Imperial College. And yeah, so the general plan is I'm going to talk a bit about parameter spaces and what's called natural families of entire functions. And then I will try to convince you that a lot of things that we might be interested in for other dynamical reasons are in fact natural families and some consequences of this. So let's get started, right? So we start with this question up here, right? So what would be the largest reasonable family, parameter family containing some given function, right? Reasonable because, of course, we can always just keep adding more and more parameters, but we want something that has some sort of like dynamical meaning, right? And we've seen before several times this week that if f, for instance, is a polynomial of degree d, then we can take something like pol d, right? The space of polynomials of degree d, which is a complex manifold of dimension d plus 1, right? Parameterized by the coefficients. If f is rational of degree d, this is a bigger sort of, I'm not going to say more interesting, but sort of like more complicated space. But it's also a complex manifold of dimension out 2d plus 1. And as we have also seen many, many times before, you can quotient these spaces by conformal conjugacies and get the famous moduli spaces, which I don't know a lot about, so this is the last time you'll hear me say moduli space, right? But so what happens if f is a transcendental entire function? Right, well, in that case, we might try a naive answer, which would be, let's just take the topological vector space of all the entire functions, right? Well, obviously, this turns out to be way too big for most anything that we want to do. And by Runge's theorem, it has polynomials everywhere. So it's very hard to talk about any sort of like structural stability or other things that we might want to look at inside this very big space, right? And so as James pointed out in his talk, there's a much better answer, right, which is this M sub f, right, which is the quasi-conformal equivalence class of f, which James has already defined for me. But we defined it as a set, right? And now we want to put some sort of parameterization of this thing. So let's start with, we take a generic parameter family of entire functions, right? So we might want to say that M is a complex manifold, that each one of these guys is an entire function, and that they depend holomorphically on the parameter lambda, right? That's our ideal of a parameter family. And we say that this parameter family is natural if there's some base point in M and quasi-conformal maps psi lambda and phi lambda such that we can write each f lambda as this funny expression here, right? So each f lambda is quasi-conformally equivalent to f lambda naught by these guys, and they depend holomorphically on our parameter, right? So we took this big thing, right? This big set here, MF, that James already talked about, and we're taking like holomorphic slices of this thing, right? So now we can talk about some kind of parametrization. And now I'm not sure, I'm not sure if this slide is strictly necessary, which is why it's in quotation marks, but I want to try to convince you that this set has some very nice properties, right? One of them is that for every G inside this equivalence class, the set of singular values of G and F, well, it's very similar in some way. You should take this to mean that there is a QC homeomorphism that takes one set of singular values onto the other, and it preserves the type of the singular value, right? So it takes critical values onto critical values, asymptotic values onto asymptotic values, and accumulation points onto accumulation points. So these guys really do have, up to a QC homeomorphism, the same singular values, right? And if F has finite non-zero order, for the people who don't really do transcendental dynamics, the order is sort of like how fast this thing grows. Then so does every other function inside this class, right? This was proved by Epstein and Rempe in 2015. If the set of singular values is bounded and the function is hyperbolic in a sense that I will not define because it isn't really relevant for us right now, then F is going to be structurally stable inside this equivalence class. Right, this is due to Rempe and Sixsmith a bit later. As James pointed out in his talk, also if S of F is bounded, then you have some sort of like model inside each equivalence class of what the dynamics escaping to infinity might look like. And I forgot to add that on the slide. And a very, very important thing about this equivalence class is that if we ask for a bit more, right? So we ask for a finite set of singular values, then it was shown by Eremenko and Lubitsch that this is a complex manifold of dimension q plus 2, right? Which has very important consequences like the no-wandering domains theorem, and also that, in particular, this guy is sort of like the whole thing is a natural family parametrized by itself, in some sense. And furthermore, this is a more recent result. Any well-behaved parameter family, which means that it satisfies all the things in the previous slide, and also singular values move holomorphically, that contains F, where F is again of finite type, is also in some sense inside this equivalence class, right? Which was proved by Matthieu, Anna, and Nuria, right? So in some sense, these equivalence classes, they have a lot of nice properties, and they are related to many of the usual parameter families that we're interested in looking at, right? And what I'm here to convince you of is that for any transcendental entire function, this equivalence class is a natural family. And furthermore, if there is some point on the complex plane that is not a singular value, then it is a complex manifold, and it has finite dimension if and only if I have finitely many singular values. Yeah. Yes. Yeah. Yes. Yeah. I should add, I forgot to add this, but that's a sort of a very good comment. Because yeah, this should be taken sort of like locally, as in around any point inside this thing, you can write it like this, right? And then, but then sometimes, for instance, if there's some winding going, if M is not simply connected, sometimes you might have like to stop and start again, right? So that's the thing that might happen. Okay, so now let's see if I can manage to convince you of this. How am I doing for time? Okay, I have good time. Okay, so we start with a very, very naive thing. They were trying to like hit the whole equivalence class at once, right? So we take this guy, MC, which is the complex manifold of Beltrami coefficients on C, right? It's a complex manifold because it's basically the unit ball in a Banach space. And then now we're going to do something like this, right? We take a Beltrami, right? Can anyone see, or should I write bigger? It's fine. Okay. So we're going to take some Beltrami coefficient in this, and we'll assign to it the unique QC homeomorphism that fixes 0 and 1, right? It's given to us by the measurable Riemann mapping theorem, right? And now I will take this guy and post-compose it with some other two parameters. Right, so that this thing here, right, is a QC homeo, and it sort of varies over all possible QC maps of the plane that integrate this Beltrami coefficient, and in particular, as this Beltrami coefficient varies in here, this thing is basically giving me all possible QC maps of the plane, right? And then now I will take my function f, right? It's here. On this side, I'm going to put this. Well, I'm going to call this guy psi sub lambda, right? And then, well, this guy is going to have its Beltrami coefficient mu, right? So on this side, I have the standard complex, the complex structure mu. And if I pull this back by f, right? So on this side, I'm going to put the complex structure f star mu. Then, well, the map that goes on this side is sort of uniquely defined if I want the function on this end to be entire, right? It has to be some map that integrates f star mu. And then all I have to do is, right, so I'm going to get like phi f star mu. But then once again, I want this to like vary through all possible QC maps that integrate this. So I'm just going to add another two parameters here, like a fine map to make this thing really vary over all maps with this Beltrami coefficient. Right, and in doing this, I get this sort of very naive function that takes me from this space, right, which is basically the Beltrami coefficient plus these four guys here, onto the equivalence class, right? And because it's so naive, it is going to cover everything, so it's surjective, and it's sort of analytic in quotation marks in the sense that it's continuous relative to the topology of V, right? The topology of local uniform convergence. And for any fixed Z, this is going to depend G. Well, let's say that for any fixed Z, G, which we can also just call F lambda, F lambda of Z depends holomorphically on lambda, right? So this is what I mean by analytic here in quotation marks, right? Okay, but well, the problem is now that this guy, right, this function here is a bit too clumsy, right? Because this space is too big. So the fiber is going to be just massive. And so what we want to do now is project down to some more manageable manifold, right? That will give us a bit more information, right? So we start from here. And so for now, we have this very naive map on term F. And what I want to do is project this down to something and then fill in this arrow and well, this arrow, right? Okay, so how are we going to do this? And Caroline, I have to apologize for this slide, right? But the basic idea here is that for functions of finite type, what Eremenko and Lubitsch did was that locally you can parameterize this equivalence class by following around the singular values, right? So if you have, say, q singular values, moving them around independently gives you q dimensions. And then if you move the whole thing together, that gives you the two extra dimensions of the conformal conjugacy. Right, so I apologize, Caroline, but we'll be parameterizing by singular values in this talk. Locally. Okay, so we want to try and sort of mimic that in this case, except that we might have like a whole bunch of singular values, and it's not so obvious that you can sort of move them about, and this will give you something that has some sort of complex structure, right? So we're gonna do the following, right? We'll take any QC maps that fix 0 and 1, right? And we'll say that they're equivalent if this composition here is isotopic to the identity relative to the singular values of f, right? So basically, if I can sort of homotopically deform one map into the other while keeping the singular values fixed, right? So in particular, these two functions sort of agree on where they should send the singular values. And now the question is this quotient here a manifold, right? And now sort of a miracle happens, and the answer is yes, right? This quotient is a complex manifold. This was shown by Mitra, who was a student of Clifford L, building on work of Gregory Lieb, who was another student of Clifford L. But the upshot is that this guy is a complex manifold, and the projection, right? So you can sort of guess that it's going to go here somewhere, right? And this projection here, given by the equivalence relation, is holomorphic, and it also has this very nice decomposition here, that it's basically the Bertrami coefficient supported on the set of singular values times the Teichmüller space on everything else, right? This might show up later. And furthermore, there is some universal holomorphic motion of the singular values over this manifold T, right? Universal here meaning that any trivializable holomorphic motion of the singular values lifts to T. I will not define what trivializable means, but any holomorphic motion that we encounter here will be trivializable, right? So, okay, so now we have some sort of quotient here that gives us a lot more information about how the singular values are moving, right? And the next step then is to show that if I take two different points in here, right, then I can define a quotient from this big space to this smaller space such that this function agrees on those points, right? And this is a proof that goes, for those of you who delved into the original paper by Eremenko and Lubitsch for functions of finite type, it's a very similar proof, right? You use some homotopy lifting arguments, yada yada, together with this nice bit of information here. But you can show that this function agrees on these points, which means that this function, this very clumsy naive function that we had, projects down to something more manageable that takes us from this more manageable manifold into the equivalence class. And because this projection is holomorphic, this guy is going to inherit all of the nice properties that this function had, right? So basically, what I have just sort of waved my hands to show is that for any transcendental entire function, this function here, right, that we just got, is analytic in the same sense that this guy was analytic, right? So in quotation marks, if I have any natural family that contains f, right? So if say I have some other lambda down here, and here I have the natural family, then there's going to be a lift in here that makes this part of the diagram commute, right? So in this sense, we can say that this function, which you notice also defines a natural family from here to here, is universal, right? It's sort of like the biggest possible natural family that contains f. And furthermore, and this is this bit is like almost magic. This function, right, from here to here, has unique path lifting, right? Which means that if down here I take any sort of continuous path of functions, starting at some point. Then on this side, if I fix any point on the pre-image of my starting point, let's say that this is G, right? And then up here I fix some point on phi minus 1 of G, right? So this is G, G tilde in this set. Then this path lifts to a unique thing up here, right? Which in particular means that, well, as I said, the equivalence class has now been turned into this sort of universal natural family, parametrized by, this is getting a bit cluttered, parametrized by this manifold here. And this map, right, the map that does the parametrization is very, very, very close to being a covering map, right? Because it will be a covering map if it has the path lifting property, and furthermore is a local homeomorphism, right? Let me see. I'm doing pretty okay for time. So I'll try to give a sketch of what goes into proving the path lifting, right? Or, well, the uniqueness of the path lifting, which is sort of the important bit. Can you erase this, I think? Okay, so now how do we prove path lifting, right? Well, the fact that path lifts exist follows from this machinery of Mitra that I mentioned before, and I won't really get into. But the uniqueness of the path lifting uses this very nice argument, right? This very cute thing that basically, if I have some function here, right? Let's say that this is some g in MF, right? And this is phi. And if I see up here something continuous, right, some continuous path, let's say gamma, that's sitting in this manifold, and such that phi of gamma of t is G for all t in 0 and 1, then gamma is constant, right? So basically the picture should not look like this, right? This is not allowed. This lift has to be a single point, right? And the idea behind this uses some results by Nuria and Christian Henriksen when they talked about Teichmüller spaces of functions with Baker domains. And the basic idea, the 30-second version of this idea, is that, well, if I manage to find this path that should not be, right, then this basically means that I have found myself. Now this is psi of t, this is phi of t. I have found myself some maps phi t and phi t that move continuously with t and make this diagram commute, right, for all t, right? And now the basic idea is that even though on this side of the diagram, the singular values might be sort of like very close together, right? So if this is like the singular values of f, they might be very close together, right? And notice that because this diagram commute, psi t has to send singular values into the singular values. On this side of the diagram, the relevant pre-images of the singular values, which are the critical points and the asymptotic paths, the social distancing, basically, right? That there's some separation between these guys that tells me that phi t, which also has to map this same set of like pre-images of the singular values into itself, cannot permute them, right? Because it has to do so continuously, and because there's like some separation, it cannot manage the jump, basically, right? For critical points, I think anyone can sort of see how it goes. For asymptotic values, it's a bit more complicated, and if I have time at the end, I might come back to this. But yeah, that's the basic idea, right? It's social distancing of preimages of singular values. Okay, so what can we do with this nice thing that we have? And the basic idea is that now, let's assume now that there's something on the complex plane that is not a singular value, right? And well, under this further assumption, we can show that actually this map is a local homeomorphism, right? Which means that around every point of this manifold, right, around every point in this manifold, there's some neighborhood where the map is a homeo onto its image. And therefore, right, because covering maps are so nice, and this one is even nicer, I can use phi to sort of transfer the complex structure from this guy to this guy and turn it into a complex manifold, right? And well, obviously the complex structure will make this guy a holomorphic covering. And so now what's the dimension of this guy down here? Well, if this is a covering, then it's exactly the same dimension as this guy, which, well, we can use, well, there's one term which is the dimension of this bit, another term which is the dimension of this bit, and a +4 that comes from these guys here, right? So in particular, right, and now we can do a sort of a reality check. If I have only Q singular values, well, then I cannot support any Beltrami coefficients on a finite set, so this guy is 0. This Teichmüller space is the Teichmüller space of the sphere minus Q plus 1 points, which, as Rohini pointed out, has dimension Q plus 1 minus 3. And then with this +4, this becomes Q plus 2, which is exactly what it should be. Right, so we're doing pretty good, it seems. And so basically, a summary of this, wait, before I do the summary, how am I doing for time? Oh, wow, I have so much time. Okay, so I'm gonna try to give an idea of why this guy is a local homeomorphism under this extra assumption. And it's a pretty cool idea, I think, that uses a very nice quasi-conformal surgery. And the basic idea is I'm going to take some point, right, some parameter lambda inside this space. Right, this is phi, and this is g, which is phi of lambda. Right, and well, now if I want to show that this is a local homeo, then with like the uniqueness of the path lifting, the only possible obstruction that I can have would be if I had some sort of like series of pre-images of G that accumulate at lambda, right? So I'd have this sequence lambda n going to lambda such that phi of lambda n equals G, right? But now, with this extra assumption, a very cool trick that we can do is we can take any one point on this sequence, and if it's sufficiently close to lambda, where sufficiently close depends only on who lambda is, then I can join it to lambda by a continuous path, right? A continuous path that also lies in the fiber, which by the lemma that was here before and that I erased is a contradiction, right? And so we get that this sequence cannot exist, and our map is a local homeo, and therefore a covering map, right? And the really cute bit is how do we construct this this little purple path here? Well, we're going to take right our favorite commuting diagram. This down here is, well, sorry. Basically, here you have G, here you have G. And the basic idea is we're going to take our favorite commuting diagram, and if there's something in here that is not a singular value, right, I will find something in here in C that is not a singular value, right, and I will put some small disk around it, right, and because these maps are converging to the identity as lambda n approaches lambda, psi lambda n is going to be very close to the identity on this little disk, right? So here we have like almost the identity. And so what I'm going to do is I will cut out an even smaller disk around it, where I will actually replace psi lambda n by the identity, right? So inside this little purple disk here, my map is now the identity. And I'll do some nice QC interpolation on this yellow annulus here. And now, well, to fix things on this side, right? Because this small disk is not in the set of singular values, its pre-image consists of countably many disks, which are all mapped homeomorphically to this disk, right? I pick any one of them, right? And oh yeah, and phi of lambda n has to permute. Let's sort of divide things here. Phi lambda n has to permute these disks sort of with themselves, right? It has to enact some permutation of these disks, right? But this guy is also converging locally uniformly to the identity, right? So if lambda n is very, very close to lambda, there is going to be some disk on these pre-images which has to be mapped onto itself, right? And now, because I did this surgery, inside some smaller disk in here, I can also cut it out and replace by the identity, right? So that now this guy is the identity on a little disk, and this guy is the identity on a little disk, and now I can take these guys and deform them continuously onto the identity, while still making sure that they are the identity on these little disks, and then by the identity principle, this gives me a fiber over G, right? That's sort of the 5-minute version of it. I'm sorry for the drawings; they're not the most accurate, but that's the general idea, right? And so with this argument, so basically the idea is that I might not have much control over what psi and phi are doing, like very, very far, right, very near infinity, because they are only moving locally uniformly with lambda. But if I restrict myself to some compact bit of the plane, I can have a lot of control over what they're doing, and that will give me this continuous fiber, and that is what gives me the local injectivity, which gives me the covering map. So to summarize all the things that I sort of waved my hand about, for any transcendental entire function, I can find some nice complex manifold, which is this thing here, and some nice map from here to my equivalence class that turns it into a natural family, right? And in this natural family is universal in some sense. And furthermore, if I have some point that is not a singular value, then this nice map is in fact very nice, and so nice that it's going to turn my equivalence class into a complex manifold. And I think I will stop here. Thanks for your attention.
Thank you very much, Gustavo. And please, it's time for questions. So are there any questions? Nikolai.
Yeah, thank you for your talk. I was curious about like topology of these spaces. So maybe even I will be more restrictive. So let's take finite type maps. And well, in this case, this MF, like, well, it's just collection of maps and we can pre and post compose them by affine maps. And now we can like quotient out, you know, this affine pre and post compositions. So roughly speaking, we remove this C star times C square factor. Yeah. So in this case, we go like from the manifold of dimension Q+2 to Q-2, because, well, every affine thing kills like 2 dimensions.
But you go down to Q, right? Because you can't kill.
I don't care about dynamics, so I don't do conjugations. I do like pre and post compositions.
Yeah, then you go
so
to
yeah. So then if you have like 3 singular values, we are left with dimension 1 thing. So it's just like Riemann surface. And can you say anything what, like, I don't know, it's Venus or whatever? I don't know.
I cannot, but that is a very good question, and I wish I could say more about it. I can sort of wave my hands into some of the ideas that we would go into describing the topology of this thing, right? Because, well, let's look at what we have on this side, right? This guy here, right, is well, it's this thing, right? So it's the product of a ball and a Teichmüller space, both of which are contractible. So this bit is very nice. This bit has some holes in them.
Yeah, but I think I quotiented it out.
Yeah.
Yeah. So it's covered by Teichmüller space in particular.
Yeah. Yeah. And then when you quotient, right, you have to, well, then what you have to do is find out like the deck transformations of this thing, basically. And my hunch, I haven't been able to prove this formally, but I think that the deck transformations are related to the symmetries of F, right? So basically, what are the affine conjugacies, right? What are the automorphisms of C such that F of sigma equals F, right? Something like this. I mean, this should definitely be in the fiber, and I haven't managed to prove that there should be like all that there is in the fiber. But yeah, and then, well, what can these guys be, right? These guys can be like an infinite cyclic group, which will give you, which will then like take some straight line up here and sort of wrap it around, which might make this thing not simply connected. Or they might be like finite cyclic groups, which I think if you have already quotiented out things like this shouldn't really happen. But I think, but then they would like wrap around this hole a finite number of times, basically. So yeah, I think, like waving my hands, that's how I would tackle this question. But yeah. But that's a very good question.
Thank you.
That I would very much like to answer.
Okay, any more questions and comments? Matthieu.
Thank you. So I think in your definition, if instead of just marking the singular value set, you mark other. So if you mark, for example, a cycle, or if you have, let's say, a finite singular orbit, and you mark it, this is more or less Adam Epstein's deformation spaces. And I think if you can sort of also mark all of the Joule set, and then you get more or less the Teichmüller space, the dynamical Teichmüller space.
Yeah.
So have you tried thinking about marking some points besides the value set?
Well, this is all very recent, right? So we're just trying to make sure that all this works, and then sit down and think about what other things we want to look at. But definitely like because the Teichmüller space, in some sense, it's going to like sit in here in some way, right? So this guy like contains the dynamical Teichmüller space of F, right? So then so many questions like what's the codimension of this thing in here? I don't know. What's the geometry of this thing in here? I don't know. But yeah, definitely lots of things to be said about how the Teichmüller space is sitting in there. So sorry, my answer to your question is basically, I don't know, but I would very much like to.
Any more questions or comments? No? So thank you very much for this very nice talk, and to all the speakers of the day.